Right, well let's make a start, given it's 8 o'clock, and some of the things I'm going to show you a little bit later go for a fair while. So those of you who are here or are going to soon be here, welcome to the May meeting of the Mornington Peninsula Astronomical Society. And what you're seeing on the front slide here is the fourth flight of the Ingenuity helicopter on Mars. And what you're hearing, audio at the moment, is what was picked up by the Perseverance rover about 60 to 80 metres away, actually listening through the Martian atmosphere to the helicopter taking off. And you can see it there on the loop video. The helicopter sort of takes off, flies off to one side out of screen, and comes back, and you're hearing the whir of the rotors, and after it lands you can hear them power down. Now that's even through the very, very thin Martian atmosphere. So you hear the rotors powering down now on the ground. The one down on the bottom left side was the uncontrolled re-entry of the Chinese Tianhe 5B rocket that could potentially have landed on Australia. What was showing on this graph here is the predicted path a couple of hours beforehand when it came in, re-entered to Earth's atmosphere. And as you see, there was a reasonable chance of it going over Perth and just south of Victoria as well. But at the end of the day, it ended up ditching in the sea near Madagascar. So even this prediction, as you can see here, Madagascar is still a fair way away from that predicted line, and that's where it ended up going down, in Madagascar. It received a bit of criticism from NASA because it came in an uncontrolled manner, and that was probably a little bit rich, given that the Skylab did the same sort of thing and landed in Australia a few decades ago as well. On the right hand side, whereas that one was a bit of a Chinese failure, the one on the right hand side so far has been a Chinese success. They've landed their first rover on Mars, and that image is obviously not one that was taken itself, because they would have had to have landed another craft to take a picture of it. That's the Zhurong, which is Chinese for a god of fire and war. And in fact, online, if you look at some of the news footage of the landing, they actually show the thing coming down, and of course you realise that can't be so, because they would have had to have landed on Mars first to put a camera in to see this thing coming down. And in fact, the footage that they showed was actually pretty amateur, and it was very, very obviously made as a simulation, but nowhere nearly as good as what you're used to seeing come out of America, for example, or even Russia. And certainly not to the European Space Agency either. Now what I'll also show next is some images of the two rovers that are on Mars. So the Curiosity rover is still functioning on Mars, as well as the new Perseverance one. The Curiosity one has sent back images of evidence of water on Mars from the crater that it's within, the Gale crater, and you'll be able to read some of that in a moment. This goes for about 2 or 3 minutes, and so I'll flick over to that now, all being well. So this is the previous rover, the Curiosity rover, which is still functioning.
Is that the Martian Symphony Orchestra playing there?
Yes. Very far in the distance, you can hear it through the thin atmosphere, yeah. Notice the rock at the top there is a mixture of cemented large and small conglomerate, as they would call it here on Earth, which is pretty good evidence of a flowing water in the past, or at least flowing liquid.
similarity in the stones.
And this is not what they found, this is what they think occurred a long time ago, when there was actually liquid water running on Mars from that particular crater.
There was definitely water there, it's just dried up over the earth.
Now you can see on this image the tracks of Perseverance rover on the right hand side there in the sand, very, very clearly seen.
Peter, obviously Martians had climate change.
Significantly so.
They should have listened.
The Martians should have been more aware.
Exactly. That's what they came to live, no doubt.
Right, so we'll move on to tonight. So if there's any new members here, welcome to the Society, and we'll try and make you as welcome as we possibly can. Our new members officer is sitting at the back of the room, ready to grapple you on the way out. But do feel free to say hello at any stage. Now, as usual, I go through the events that have occurred since we last met here last month, and what's coming up in the immediate future for things that the Society is doing. Then I'll show a very good talk from the Royal Institution in London by Professor Lucie Green, all about the structure of the Sun, how the magnetism of it actually works. And the key to all of this is coming up with the aurora. So you'll see some of the other videos that we'll show after the tea break, after Mark's done Sky for the month. We'll show a little bit about Michael Collins, about a 9 or 10 minute video about him. This was actually taken at the 50th anniversary 2 years ago. Michael Collins, the third person to go around the moon. Didn't actually go down to the surface with Neil Armstrong and Buzz Aldrin, but he passed away 28th of April. So Buzz Aldrin is the only one surviving of that crew. He actually died of cancer, though I don't think they published online what specifically what cancer. Then we'll look at how to photograph a lunar eclipse, and of course there's a lunar eclipse coming up on the 26th of this month, which is not too far away, and indeed there'll be an event held here at the Briars. There won't be a talk at that, it'll just be outside looking at the eclipse. Then I'll explain a bit about the Parker Solar Space Probe. This is the one that's been sent to go really, really close to the Sun, and in fact last week the Parker Space Probe beat the all-time record of the fastest things that humans have ever built. It exceeded 500,000 kilometres an hour. And what it's been doing is it's been using the slingshot effect to go between the Sun and Venus, getting more and more speed in the process, and it's going to be even faster by the end of the year. So it'll absolutely smash its record at that time. They sort of quoted in terms of it'll take 4 minutes to go around the Earth once. You know, it's going at that speed, so it really, really is battling along. Then we'll look at a little bit about the science behind the Northern Lights. I couldn't find anything on the Southern Lights specifically, so I showed the Northern Lights. They make a little mention of the Southern Lights, but the Aurora Borealis, or the Northern Lights, behave exactly the same as the Southern Lights. The only difference is the land areas in the Northern Hemisphere are closer to the poles, the magnetic poles of Earth, than we actually have ready access to here in the Southern Hemisphere. Then after that we'll look at Steve, which is a special kind of aurora, and give you a bit of background on what Steve is. And then we'll look at an interesting one from an online physicist, Maggie Liu, about what actually causes an aurora, and she goes into some detail there, not only auroras on Earth but also on the planets. Then at the end we'll close with a bit of a sea shanty, given that there's been a lot of sea shanties during the lockdown in the past, and this one was released by NASA just a few days ago. NASA Goddard Space Flight Centre, so hang around for listening to a bunch of scientists sing a sea shanty, or try to. Recent events. Now that photograph on the back there was taken by member Paul Albers from Balnarring, and a wonderful image it is of the Aurora Australis on the 12th of May, so exactly 1 week ago yesterday or last night. So that was about 11 o'clock at night, visible to the naked eye as well, so it wasn't only camera. And you see wonderful reds there, and wonderful structure down the bottom here. So you see these lines of greeny yellow light, and you can also see some rays pointing upwards, fingers pointing upwards from the southern sky. So this is looking pretty much due south, and very, very impressive that he managed to get that in such a nice image. Last committee meeting we had on the 28th, we talked about a few things. One was about the meteorites. The meteorites have actually turned up that the Society ordered, and one's probably still in bubble wrap. And Jamie Pole has been expertly trying to get this through customs for weeks and weeks and weeks. It came all the way from space without any trouble, and then getting it from America proved a little bit more difficult. So this is another example of the Campo de Cielo meteorite that landed in Argentina, and the idea of this is so the Society has something to take to talks and presentations, and indeed in August there's going to be a special presentation all about shooting stars that Trevor's been working on to go with that. And then we'll have it on display here as well. So if you want to have a little look at that a little bit later on, feel free to come up and have a squeeze. It spent more time sitting in customs in Melbourne, waiting for the right procedure and code than it did to come all the way here from America, even with the current restrictions in place on international travel.
Yeah, there's no planetary control.
Clearly not. Clearly not. Society is also lined up for a grant for some audio-visual equipment, which, amongst other things, will hopefully go in this room to make it a little bit more friendly on both the audience and also the presenter as well. And the committee was talking also about looking at the toilet area at the front as you came in from the car park. Maybe putting a gate at the front there, much like you have at Greenwich Observatory, for any of you who've ever been to Greenwich Observatory or seen Greenwich Observatory, because the Briars here has actually had some trouble with people vandalising things on site. Now, we haven't had the same issues here on the observatory, but the Briars has been supportive of us putting in like a wrought iron type gate or that to stop casual walkers through, just in case it actually ends up being an issue. And indeed we have had issues here not too long ago of the public turning up about midnight, for example, unannounced, and you have to sort of think, okay, what was the intention there? On the 5th of May we went down to Camp Mannion in Sunnyside Road in Mornington for St Augustine's Primary School, and they had a good clear night for that one, and we had 75 Year 5 students, so primary level. 7th of May we had the public night here, and it was cloudy for most of the time, varied a little bit throughout the evening, and Manfred gave his first talk with the solar system slides for the Society, so we welcome him to the club of speakers who can speak at public nights and scout nights and all those sort of things as well. Last night we were at Parkdale Secondary College up in Mordialloc Way, even though it's called Parkdale College. Maybe it was Parkdale at one stage and the boundaries changed. We actually ended up with 155 students there, all Year 7s. And we had to do things a little bit differently because the skies had a lot of cloud to begin with. We could see the moon initially, but the prediction from the Bureau of Meteorology was that it was going to cloud over completely, like within the hour. So we did it around the other way, did the telescopes first, and then they came inside for the talk. And then they kept me talking to about 8:30 and asking questions before we let them all go home. And coming up, there you see Manfred over there giving his talk up here at the podium at the public night. Coming up is this Saturday, members working bee, followed by a barbecue here at the Briars. So any members are welcome to come along to that as well. Next week we've got a school night at Mount Aaron Secondary in Frankston, and Catherine will be doing a bit of a duet with me. Yes, Fred?
That lunar eclipse, has anybody got a long range weather forecast to see what sort of a night it's going to be at all?
Yes.
Is it going to be clear?
I can't tell you, but yeah, so, someone would have a forecast, yes.
Okay.
Yes. Then the night after, on the 26th of May, will be the lunar eclipse here at the Briars, and I think it goes from about 6:45 and until about 11 o'clock, I think, is the last point throughout. It's a fairly shallow eclipse, but the moon does actually go entirely into a shadow. It's just not right into the dead centre of it, so you're not likely to get a really, really dark red, brick red, sort of grey moon, but it should certainly turn an orangey or a coppery colour, I would think. And that Friday, 28th of May, we've got the Scouts, Cubs and Guides here, and we've got a group of Mount Eliza Scouts coming down for that one. Another one at Mount Eliza Secondary College will be coming here to the Briars on the 2nd of June. This is one of the schools that had to cancel last year because of the COVID situation, so we were due to have them then, but because of lockdown they had to be put off. Then we've got a Year 10 work experience student again here at the Briars, starting that same week as well. In fact, her first day here at the Briars is our public night, that very night, so I'll try and convince her to stay on and actually help for the public night as well. Maybe drag her parents in as well. Trevor will give the talk this public stargazing night, and our next committee meeting has had to be delayed by a couple of weeks because otherwise it clashes with other things that are on the calendar as well, so that's why it's a very odd date shown there. So for tonight's talk we'll look at Lucie Green here, and she's an interesting character. She's a solar physicist from University College of London, and she's married, and their wedding rings were made out of meteorites. So they cut them out of nickel-iron meteorites, and so she wears those proudly as she talks. Now this talk and the questions and answers that go with it will probably go till about 9:30 or thereabouts. So you see the clock over to the right hand side on the wall there. If you feel like getting up and getting a cup of coffee, don't feel pressured to be stuck to your seat. Just quietly go out the back of the room. I would also remind you, if you haven't already done so, please QR code in, so as the authorities know who's here, just in case there ever is an outbreak of anything here COVID related. Now, hopefully this is not going to be too loud.
Thank you. Yes, it is an absolute pleasure to be here tonight. And I've been wanting to come and give a talk at the RI for a long, long time. So this fulfills one of my ambitions in life. And I'm extra pleased to be able to come and talk about the book that I've been writing, 15 Million Degrees. So I'm going to talk about the book tonight, which means you don't have to buy it if you don't want to. I'm going to tell you what's in it. Sorry, Penguin. But what I want to do is convey, first of all, where we are with modern solar physics research. What are some of the interesting topics that we're focusing on at the moment? But then make the most of the fact that we are here in this very significant building, and this spot is very significant for scientific developments and the publicity and the public engagement around science too. So when I was writing this talk, I thought, right, I must go and have a rummage through the RI archives. So I did that, and I spent half a day looking through Michael Faraday's work and many other people's work, reading the Friday evening discourses that have been held here. And I would encourage you to do the same as well. You are all free and able to book an appointment and have a look through the archives, and it is an amazing thing to do. So some of the things I found out during that visit are in this talk. And I want to sort of convey a little bit about the history of science and then how we've got to where we are today and what that means for us in modern solar physics. So it's been a lot of fun writing this talk. It's been a lot of fun writing the book. But I also have an awful lot of fun doing the research too. And that's what I want to talk to you about really this evening. So when it comes to talking about the sun, I have to show photos, images that we take, particularly from spacecraft. And I always find it quite good to start off with these kind of images, which show the sun as we see it in visible light. So this is how our eyes see the sun, the wavelength of light that our eyes detect. And actually, this image is one that's been taken by NASA's Solar Dynamics Observatory. It's been in orbit now for just over 6 years, and it is the telescope or the suite of telescopes that give us the highest resolution images of the sun. So this is the visible light images. We see sunspots on the surface of the sun, which the number of which vary in time. So some of you may have heard about the solar cycle, where the number of sunspots rises and falls over a timescale of around 11 years. So this image, this is an old one now, actually from a few years ago. And we've just come through solar maximum, and we're on the declining phase of the cycle now. So we can look at the sun in visible light, see features on the visible surface. But I'm a space scientist. And so the view of the sun that I enjoy and that I use in my research is the view that we can only get by going above the Earth's atmosphere. And that means we can see all of the sun's radiation, from radio wavelengths all the way through to gamma ray radiation as well. But if we look in ultraviolet light, that's where I think we see some of the best views, some of the most attractive views of the sun. So if I was to show you the sun at exactly the same time as this image, but just using a different wavelength of light, it looks like this. Oh, excellent. I do love that response. I hope to get perhaps 1 or 2 more oohs out of you as the talk goes on. So this is the sun's million-degree atmosphere that we call the corona. You can see it has a completely different shape and structure to the photosphere that I showed you before with its dark sunspots. Now you see what looks much more three-dimensional. And that's because the light being given off from this layer, well, the light is coming from a layer that we call optically thin. So photons all through this gas can make it out and reach our telescopes. But what you're looking at here is light in the ultraviolet part of the spectrum, in the extreme ultraviolet part. So we can't detect this light from the surface of the Earth. We have to go into space. So we gather light across all of the wavelengths, but we don't just use the light to take images. I mean, my research focuses a lot on the images, but some of the instrumentation that we build at UCL uses the technique where you split the sun's light up into a rainbow. So in the sort of very basic sense, you might think about the prism, sunlight coming through a prism, perhaps as Newton did in the 1600s. The sunlight comes through, splits up into the rainbow. You could display that in a different way, and you could say, right, I'm going to have wavelength running along the horizontal axis, going from short wavelength blue light to long wavelength red light. You could even plot a graph to show you how much light you have at different wavelengths. So this might look something like you have on the screen now. So this is a plot, just a sort of schematic showing that you might have different amounts of light at different wavelengths or different colours. So what you're looking at here is something that we would call a continuum, which is a sort of curve, but then superimposed on that, you have what we call spectral lines. So in this case, dips in the amount of light, but they could also be spikes in the amount of light. So we would say absorption lines or emission lines, depending on whether light is being absorbed by gas in the sun's atmosphere or emitted by gas in the sun's atmosphere. So I just want to sort of introduce this as a technique that we can use to learn more about the sun. Looking at this particular part of sunlight, the visible light, gives us an idea of the surface temperature of the sun, which is around 6,000 Kelvin. But you can also use these spectral lines to probe what the sun is made of, because particular atoms of particular elements absorb and emit light at very distinct wavelengths or frequencies, depending on how you think about it. So these spectral lines can be really, really important. And one of the things that we do now is not just utilise the visible part of the spectrum, but also those other parts as well. So one of the instruments that we have in space at the moment that was developed by my department, the Mobile Space Science Laboratory, is flying on a Japanese mission called Faraday that was launched in 2006. And the kind of spectrum that this instrument takes looks like this. So this is now the sun's ultraviolet light taken using a technique where you just take a narrow part of the sun's disk. So it's like looking through some shutters. The light comes through the shutters, gets dispersed, so that you can see all the different wavelengths. So if I was to then turn this into a graphical representation, into a plot, we'd have wavelength going along that horizontal axis again, and then the amount of light at different wavelengths that you see. And you see that it corresponds, those bright streaks, where we've got lots of light coming in at that wavelength, correspond to a nice spike in the spectrum. So here we have a series of spectral lines, emission lines, each one being formed by light emitted by particular atoms or particular ions in the atmosphere of the sun. So I could label these, I forget exactly what they are now, but they might be ions of iron or calcium or silicon and so on. So we can use them as a fingerprint to work out what's in the sun's atmosphere. But because this instrument is something called an imaging spectrometer, we can do even more than that. So I can take my slit of the instrument and move it slowly across the sun. And that means I can make images using my spectrometer. And I can make images at different wavelengths. And that's what you're seeing here. So these are images taken or created with our spectrometer on Hinaday that show the sun's corona in different wavelengths of light. And those different wavelengths of light map to different plasma temperatures. So going from the coolest in the sort of middle bottom up to the hottest in the top left-hand side. And actually, one of the wavelengths that you see here is a particular emission line being given off by iron 12. You can see the Fe and then the numerals iron 12, 195 angstroms. And that's the wavelength of light that I used to make the picture for the front cover of the book. So it's one of my favourite wavelengths of light that the sun gives off. It's quite sad. We sort of develop favourites, and 195 iron 12 is my favourite. So, yeah. So I can gather spectra of the sun, I can make images, and I can also make movies. So I can run this over time, and you can see this particular region evolves. And actually, this is a region of plasma above a sunspot region on the sun. But even more than that, so this image that you're seeing now has blue and red patches in it. And so as well as using a spectrum to understand what elements are in the atmosphere of the sun, we can also look for things like plasma flows, because light becomes blue shifted when it moves towards you and red shifted when it moves away from you, the same as we experience with sound waves from a moving source. So having a spectrometer flying in space is incredibly versatile and allows us to do some really good physics about the atmosphere of the sun. But as I mentioned, I'm quite heavily reliant on images of the sun. And so I want to show you some of the activity that we detect once you start looking at a series of images put together. So if we go back to this view, this is the one I showed at the start of the sun's corona, looking at plasma that has a temperature of a few million Kelvin. And I can run a movie of this. But actually what I want to show you is a movie that's been made by processing the data in a particular way. So this is the start of the movie, and it's the sun at exactly the same time, but this movie, which has been made by one of my colleagues, Dave Long, is using the fact that if you subtract one image from another, so you literally take your intensity across the image from one image to the next and do a subtraction. So any features in the sun's atmosphere that become brighter will appear as white. Any features in the sun's atmosphere that become less bright will darken. And things that don't change will remain grey. Now, this movie is slightly more complex because we've got 3 different wavelengths of light that we're using. So they're listed on the right-hand side in blue, green, and red. So we can do a little bit of a proxy about temperature changes in the atmosphere as well. But what I want to do is show you the movie, and hopefully you'll see dynamic activity revealed. So it flickers a bit as it's running before the main event happens, and you see a bright flash of light, and you see this huge eruption taking place in the sun's atmosphere. So this is a kind of activity, a form of activity that we call a coronal mass ejection. It's not the best phrase that we've ever come up with in solar physics, but it does what it says on the tin. It is an ejection of mass of plasma from the sun's corona, from the atmosphere. And these are this is the form of solar activity that I study in my research. So later on, I'll come back to how we think these things are being formed. And they are incredible. We can watch them flowing out into the solar system. So this is now the same event, but seen using a different kind of telescope. This is an instrument that creates an artificial solar eclipse. So it places a disk in front of the sun, blocks out the bright light of the photosphere, and leaves the atmosphere of the sun revealed by light that's actually scattered by the plasma. So this isn't direct emission that you're seeing here, but scattered light coming from photons that are deflected in this cloud of moving plasma. So this coronal mass ejection flows away from the sun. And it travels, I forget the speed of this one, but in general they can move between maybe a few hundred kilometers a second to maybe over 2,000 kilometers a second. And so they are fast. They carry the same mass as a mountain. So for those of you who remember your equations about kinetic energy, half mv squared, enormous amounts of energy. And it's been a big question in solar physics to try and understand where that energy comes from. So these are coronal mass ejections. And actually, incidentally, that black arm that you can see coming from the left-hand side of the image up towards the centre, that's the arm that holds the occulting disk in place in our telescope. And this is a telescope that's... actually, this one's not orbiting the Earth. This one is orbiting a point called the first Lagrange point, which is a small fraction of the distance between the Sun and the Earth. So if I have this movie and I run it again, but this time allow it to run for longer, you'll be able to see another effect come into play. So first of all, you'll see the eruption itself. Off it goes. And then as I run it further, you'll start to see these white flecks that appear in the image, and gradually a sort of snowstorm effect builds up. And it becomes completely dominant over the image to the point where you can barely see anything else. Now, these snowstorms are caused by electrically charged particles, protons, that are accelerated away from the sun at speeds close to the speed of light. They take, let me say how long the coronal mass ejection takes first of all. So I've already said that travels at 2,000 kilometers a second or more. And a coronal mass ejection takes perhaps 2 to 4 days to travel the 150 million kilometers between the sun and us. These particles, these protons, that get accelerated during these events take maybe half an hour to get to us. So they are incredibly fast. They hit our electronic detectors, they create a current, and that current is then registered by these bright specks. And actually these particle storms, we call them solar energetic particles, SEPs, again, another not particularly romantic name, but does what it says on the tin. These are the kind of events that if they happen whilst astronauts are doing spacewalks, can be incredibly hazardous. The Apollo astronauts reported having flashes of light in their eyes, even when they closed their eyes, and that was because of these high-energy particles coming in and interacting with their retina. But the more dangerous side is that if you get a storm of this ionizing radiation, you could end up with radiation sickness or leukemia, or perhaps even a fatal dose if it's really extreme. So the manned space program always looks at the sun to see what's happening so that they can forecast and get astronauts into a more shielded part of the space station should they need to. So coronal mass ejections and solar energetic particles. I just want to show you another coronal mass ejection, which is my favourite one that the sun has ever produced. And it's one that happened in June 2011. And I remember this clearly because I was at Cheltenham Science Festival at the time that these data were released. And I remember seeing the movie going around on the internet. And I didn't believe that it was real, actually. I thought someone had photoshopped it. So I went back to the NASA data archive, I got the data myself, and this is the movie that I made. So probably, if you haven't seen this movie before, you might not think the sun looks particularly special on this day in June 2011. I didn't. But there's a region on here that just did something phenomenal. So let me play the movie. So off it goes. I got a little ooh there. Yeah, good. So this remains for me the most spectacular eruption that the sun has ever produced. This time, so much plasma was thrown up against the huge gravitational pull of the sun, 27 times what we experience at the surface of the Earth. So much gets thrown up that a lot of it falls back down to the surface of the sun. And I know of many PhD projects who have carried out research on just this one eruption. So I have one student who's looking at it. So we want to understand what's driving these events. Where does the energy come from? So that's it as shown in ultraviolet light, looking at plasma that's around 80,000 Kelvin. But I can also do what I did before and show you this so-called difference movie to see just how much more detail gets brought out when you use this technique. So this again is a movie by my colleague Dave Long, and this is the same event. It's much better, isn't it? It looks amazing. I trained as an artist before I trained as a physicist, and actually I think there's something about these events that really appeals to me on an aesthetic level, that I just love to see these kind of data. So you can see this huge bubble that really rapidly expands, and then that material gets thrown up into the atmosphere of the sun. And these kind of difference movies are really useful to pick out the detail. You can see the downflowing plasma, you can see where it's crashing into the lower atmosphere, which is just a gas, it's not a solid surface. But as the gas gets compressed, it gets heated, and then it starts to glow again. So coronal mass ejections are scientifically fascinating, but also pretty beautiful to look at too. But there's one more form of solar activity that we're focusing on in solar physics at the moment, and that's something called a solar flare. And I've got another movie here. This is now taken from one of the Stereo spacecraft, which is a NASA mission. It's looking at the sun's atmosphere, again, the corona in extreme ultraviolet light. And when I play the movie this time, you'll see a flash of light happen in a region above the sunspots. So this is what we call a solar flare. And this is the form of solar activity that we've known about since 1859. A huge amount of work has gone into trying to explain, again, why these happen. When a solar flare occurs, you see a flash of light across the entire electromagnetic spectrum, from radio often into gamma rays, but certainly this intense brightening in ultraviolet light and also in X-rays as well. So solar flares are another big topic of study. This is another movie taken from the SOHO spacecraft, just showing what a solar flare can look like when it's directly along the Sun-Earth line. So in this case, sort of top middle of the sun, you see a solar flare go off. There's also a coronal mass ejection from exactly the same region at exactly the same time, but it's just hard to detect in these images. You need those artificial solar eclipse images to see it. And you have a solar energetic particle event. So we have coronal mass ejections, energetic particles, and flares happening often all at the same time. But perhaps one of the biggest discoveries about the space age has been to do with our relationship with the sun. And that's well illustrated by this animation. So this takes a bit of a setup, because what you're seeing here are images from two different spacecraft. And again, this is the NASA's Stereo mission. You'll see I've pointed to the sun in the center. So now the sun looks tiny. This is such a wide field of view that we're looking at. The sun is absolutely tiny. On the left-hand side of that image, you've got the view from one spacecraft, which has left the Earth, travelled away from us, and is now looking back along the Sun-Earth line. On the right-hand side, you've got the counterpart spacecraft, which has left the Earth, gone behind us in our orbit around the Sun, and is looking back along the Sun-Earth line. So these two spacecraft are looking at the same region of space, but from different directions. And now, if I run the movie, in fact, you can see the Earth. The Earth is in these images. That is us. We are seen by this spacecraft. So if I run the movie, you'll see immediately what I mean about our relationship with the sun. So you see a constant outflow. These coronal mass ejections, they flow out, they don't stop. They flow over the Earth, they flow over all the planets, the objects in the Kuiper belt, and they keep going until they reach the edge of what I would call the edge of the solar system, which is far beyond where the planets are orbiting. And not only do we have these coronal mass ejections, but actually because the sun is a hot, dense ball of plasma in the cold vacuum of space, it's actually got enough gas pressure in its atmosphere to overcome gravity, and the whole atmosphere at the top is expanding. And we call that the solar wind. So not only do we have eruptions, but we have a constant expansion of the sun's atmosphere that washes over all of us. The Earth is literally living in the atmosphere of the sun. We are living in the atmosphere of the sun. And it has some pretty big consequences for us. And so, sort of, maybe the impact side of the research that people like myself do is something that we call space weather. So there's a big push now, or a big drive to understand, okay, well, when these eruptions of plasma of the coronal mass ejections get to us, when the solar wind gets to us, when the energetic particles get to us, how do they deposit their energy in our magnetic field, in our atmosphere, in the surface of the Earth, and what impact does that have? So up here, I've just got listed some of the ways that these events can affect us. So coronal mass ejections in the past have caused disruptions or perhaps even outages to our electricity network. Solar flares can heat up the atmosphere, causing it to expand, causing problems with atmospheric drag on satellites. They deorbit more quickly. And energetic particles that I mentioned earlier are really hazardous for astronauts in particular, but there's also lots of work looking at, well, actually, if you're working in the aviation sector, what impact do these particles have on human health for people who are working on aircraft, but also for the miniature electronics on aircraft themselves. And so myself, my colleagues and scientists around the UK are all working on trying to understand what does this solar activity mean for our everyday lives. And very recently, the Met Office set up a space weather forecasting centre. So you can go to the Met Office to know whether you need your umbrella tomorrow, and Tim Peake can go to know whether he needs his, I don't know, metal umbrella tomorrow as well. So there's a huge amount of investment, but for very good reason. So that was my kind of intro section to show some of the solar phenomena that we're focusing on to try and understand. And I'm going to come back to why or how we interpret them, what the physical processes are, in the last part of my talk. But for the middle part, I want to just say a few words about how far we've come. What has the story been to get to the point of being able to understand these events? And we have made a huge amount of progress. So I was sort of reflecting on, okay, I'm giving the talk here tonight at the RI. What's been that story since the RI was formed in 1799? And I think it's fair to say that we had fairly primitive views at that point. Now, the images that I'm showing here predate the formation of the RI. So on the left-hand side, I've got a drawing of the sun made by Thomas Harriot in 1610. This is the first drawing of the sun through a telescope, or the first drawing of sunspots even. And so you can see those dark patches that he saw as he looked at the sun. Foolishly looked at the sun through a telescope directly. Never do that. Really bad idea. And it's really nice when you read his notes. He talks about looking like quickly with his right eye, and then his left, and his right, and his left. You can see why. But luckily he did. And we have this amazing drawing which shows us that the sun has these spots on the surface. But of course, they're not discussed in his writing because there was no expectation, I suppose. What should the sun look like through a telescope? And are these features on the sun or not? That was a huge debate. But I like to show this because this is a British drawing, the first record of spots on the sun. The person who's more famously associated with sunspots is Galileo. And these are his drawing of sunspots from the summer of 1612. Amazing drawings. They show structure. They show that the sun is rotating. As long as you assume that spots are on the surface of the sun, which we know they are on the surface of the sun, so you can get the rotation rate of the sun just from something as simple as looking at the spots. So, in fact, everybody in this room could do this experiment. You can work out how quickly the sun rotates, and if it rotates at different speeds at different latitudes, because you can use the sunspots to be able to do that. So, when the RI was formed, we had, almost 200 years of sunspot observations, of sunspot drawings, but there was no idea about what they were. 200 years of work, and we still didn't know what they were. And that's because our ideas about light hadn't been developed enough. So the way the sun sends us information is in its sunlight. Everything that we know, what it's made of, how it's moving, is captured in its sunlight. I suppose that, and the fact that because we live in the sun's atmosphere, we can send spacecraft directly into it and measure the particles in situ. But before we had the space age, this was the way that we were able to study the light. And it's interesting reading back about the early stories of sunspots because they all drew on terrestrial experience. And I suppose that's quite natural. When you're trying to explain an alien concept, you draw on what you know. So there's discussions about sunspots being hurricanes in the sun's atmosphere or volcanoes on the sun. I quite like the work that was done by this chap. This is William Herschel. At the end of the 1700s, and he was the person who had the best telescopes, and he was using them to look at the sun. But even he didn't know what the sun was and what sunspots are. But he has this really nice piece of reasoning that I was reading in one of his papers, so he's trying to figure out what the sun is, what sunspots are. And so he has this reasoning where he imagines an observer on the moon, and they're looking back at the Earth. And he thinks, well, what would they see? And so he thinks, well, actually, they could only see the surface of the Earth where there's gaps in the clouds to be able to see through. And then he thinks, well, actually, if they were looking at the night side of the Earth, they might see some glowing gases, the aurora. So glowing gases, glowing sun, okay? So there's glowing gases in the Earth's atmosphere. At this time, they had also made observations of other planets, of course. And one of them, observations of Venus, also showed glowing something on the night side of Venus. This is called the ashen light. So William Herschel was using terrestrial reasoning and his observations, amazing observations of the planets, to try and learn something around the sun. And he ended up concluding that a sort of planetary interpretation of the sun, where you have a glowing atmosphere, and the sunspots are these holes in the atmosphere, breaks in the hot glowing clouds where you can see down to the surface of the sun, the cool surface of the sun. And in his paper of 1795, he even has this line where he says, "This leads us on to suppose that it is most probably inhabited, the sun, like the rest of the planets." Lewis, is that true? By beings whose organs are adapted to the peculiar circumstances of that vast globe. So I think this says everything, that we really didn't have a clue. But today we do. So how did we get there? And that brings me on to the Royal Institution and the key player of the Royal Institution, which is Michael Faraday. Because what I want to talk about now is magnetic fields. It turns out that magnetic fields are centrally important to understanding the sun. And so that's what I'm going to focus on for the rest of my talk. So when I came here and I had a rummage through the archives, of course I wanted to see the work of Michael Faraday. And Charlotte New here very kindly showed me Michael Faraday's lab book. So this is one of them. This is his writing. And in this experiment, he's using a wire that he's passing a current through, and that's generating a magnetic field. So this is Ampere's law. You pass the current through the wire, and you have the circular magnetic field around your wire. But what I hadn't realized was how he had captured that magnetic field. And that's what's being shown here. So these are iron filings that he put down onto melted wax. So the wax would set, and in it would be captured the shapes and the strengths of the magnetic fields. Amazingly simple. Again, something that we could all in this room do. I just love the fact that this is so important, but so simple. And this is another one of the images or figures that he created. So again, you can literally see where the magnets were underneath the paper, and you can see the shapes in the iron filings. And this is classic school experiments investigating magnetic fields. At home, I have a pot of iron filings. It's so good. And so here you can see the shapes in the magnetic fields. And one of the things that I didn't realize for a long time is that when I talk about magnetic fields and I'm trying to convey them to a colleague, what I quite often do is draw a picture. So I would draw my magnet, my North Pole and my South Pole, and I would draw magnetic field lines in between the North and South Poles. And where those lines are bunched up, that means I have a strong magnetic field, and where they're spread out, I have a weak magnetic field. But I also put arrows on to go from north to south. So I use the concept of a magnetic field line just to show the shapes that these iron filings are tracing out. And what I hadn't realized was that this is a concept that Michael Faraday came up with to communicate about magnetic fields. And I just think it's so lovely that we still rely on it really heavily today. So at home, yes, I can be found with my iron filings, and at work I draw them, but I'm also a big fan of pipe cleaners. So with my students, we're always making shapes with pipe cleaners to show magnetic fields, or to help our discussions about magnetic fields. So Michael Faraday, huge amounts of work on electricity and magnetism, here in this building, on this spot, talking about them. I hope I'm doing him justice. And in 1845, Michael Faraday discovered a link between, or a connection between light and magnetism, so that you can rotate the plane of polarization of light when it passes through a magnetic field. But one of the other things he was working towards was to use a spectroscope. So as I mentioned earlier, we use spectroscopes or spectrometers today to split light into its component colors and look at the spectral lines. And Michael Faraday was interested in, would there be any effect on a spectral line of a substance, of an emitting substance, if it were influenced by a magnetic field? Now, his apparatus wasn't good enough to answer that question, but it's something that got picked up again or continued to be worked on. And so my story now moves from Michael Faraday to some other people who were key players in bringing us from magnetic fields in the lab to magnetic fields, well, on the sun. So the next person in the story, which is heavily condensed, is Peter Zeeman. And he was also working on spectral lines and magnetic fields. And he was the person who showed that, yes, if you had an object emitting light that was a magnetized gas, for example, that would be affecting the spectral lines. So earlier on, I showed these peaks where we had one spectral line per element or per atomic transition. But what happens when you have a magnetic field is that the spectral line splits. So it can broaden, and in a strong field it can split. So for example, you might have a stationary component at the original wavelength, and then a component either side, one at a slightly shorter and one at a slightly longer wavelength. And this is now called the Zeeman effect, after Zeeman. And it's an amazing piece of research because it means we can detect magnetic fields from a distance. If something that's emitting light is also magnetized, there's a fingerprint of that in the light that it transmits to us. So that's the first piece of information. So I'm building now towards something that we learned about the sun. The second piece of information that actually was announced right here in 1897 by J.J. Thomson, who I've shown here, is the discovery of the electron, although it wasn't called the electron at the time. But subatomic negatively charged particles. So that's the next piece of information that I want us to keep in mind. A third piece of information is an experiment that was carried out by Henry Rowland. He did an experiment where he had an electrically charged disk and he rotated it and realized that it created a magnetic field. So here again, we've got this link between electricity and magnetism, flow of electrically charged particles, and so on. So these three pieces of research come together to be relevant to our story of the sun because they were put together by this man. And this is George Ellery Hale. Maybe I could just have a show of hands if you've heard of George Ellery Hale before. Oh, yes, some people. Brilliant. I think he is the most important person in solar physics. I'm so glad that he's a name that's familiar to some people in here. If he's not, by the end of tonight, he will be. He'll be someone that you'll be thinking about. He was an amazing American astronomer/engineer. He came from a wealthy family. He had a very high-quality observatory, even as a child, that his father funded for him. But he had an amazing mind where he was able to bring together different areas of science and synthesize them together to make new discoveries. So he knew about electrons. He knew about rotating charged disks creating magnetic fields, and he knew that you could detect a magnetic field from a distance. And actually, Zeeman was also, of course, aware of this. And Zeeman was thinking, well, if the sun has a magnetic field, what I've discovered would enable us to detect it. But it takes more than that. You have to know information about the sun as well. And George Ellery Hale had become very proficient at building instrumentation to study the sun. In particular, the developments around spectroscopy and light and his engineering led him to build a telescope that looked at very particular wavelengths of the light that the sun gives off. So not the whole visible light spectrum, but different or particular wavelengths. And in the early 1900s, in 1908 in fact, he built a telescope that could pick up light from the sun in the wavelength of what we call hydrogen alpha. So this is light created by a particular energy transition as an electron falls to a lower energy level in your hydrogen and gives off light. And we call it hydrogen alpha. And it's a really important line for observing the sun even today. And this is the image that he created. So this is now looking not at the photosphere of the sun, not at that visible surface, also not at the corona high up, but at a layer in the middle that we call the chromosphere. And you see a huge amount of structure. You can probably just about see some sunspots on the top right and one down right in the centre in the bottom. And then also this snake-like feature that we call a filament in the sun's atmosphere. And Hale noticed something curious about the shapes in the sun's plasma. So he knew by this time that the sun was hot gas. So the elements, the atoms would be torn apart. So he thought probably, yes, there are electrons freely floating in the atmosphere of the sun that have been torn away from their atoms. And he noticed something else. And I'm going to show you a modern image now to illustrate something that caught Hale's eye. So this is a modern image of the sun taken in the light of hydrogen alpha. This is actually an image taken back in April this year. So April this year, when we had an enormous sunspot crossing the surface of the sun. And I don't know if anyone in this room went out and saw it. Yes, you saw it. Did you have Eclipse viewers?
Photographed it as well.
Brilliant. Have you got that photo with you? Oh, I see it later. That'd be brilliant. So this is an amazing event. So we get so excited. Large sunspot appeared on the sun, and it was visible to the naked eye if you had filters. So we all went outside and put on our Eclipse viewers and looked at this sunspot. It was amazing. And it was interesting. So I had a new PhD student at the time, and he was saying, I can't see it, I can't see it. I was like, right, I need to train you a bit more. So next time this happens, he will be able to see it. So this is the sun in hydrogen alpha. This is the visible light image just to show you that sunspot. It's absolutely ginormous. For size, as a context, you'd fit 110 Earths across the width of the sun. So this is many times the size of the Earth. This sunspot, absolutely enormous. But this is at the same time in the light of hydrogen alpha, just picking out a narrow spectral range. And then if I zoom into that sunspot region, hopefully what you'll see is that you've got the dark sunspot, but you've got these sort of spiral, like Catherine wheel sort of features around the sunspots. And Hale called these solar vortices. So he was looking at the sun thinking, okay, there's probably electrons here. There's some sort of vortical motion, and vortical motion of something charged can create a magnetic field. And if it creates a magnetic field, I know how to detect it because of the Zeeman effect of splitting of the spectral lines. And he knew how to test that because he was an amazing instrument maker. And so in 1908, George Ellery Hale became the person who had put all this information together, built the right telescope, looked at sunspot regions, and detected that they were indeed sources of strong magnetic field. So the first discovery of a magnetic field beyond the Earth, and I would say the point when solar physics really began. So 300 years after the first telescopic observations of sunspots, we finally knew they are sources of strong magnetic field. So when we look at images like this today, we know that they're magnetic field regions, and they're regions where plasma, electrically charged gas, is trapped and is able to cool down slightly relative to the surrounding photosphere. So the magnetic field and the strength of it is what creates these dark spots on the surface of the sun. And this discovery was so important. And it found an advocate here at the RI in Arthur Eddington, who was a mathematician and astronomer and very famous scientist working at Cambridge. He was the person who also supported Einstein's general theory of relativity, went on an Eclipse expedition in 1919 to measure deflection of starlight during a solar eclipse and looked at, or backed up the idea, backed up Einstein's theories. But anyway, that's another story. So in 1909, Eddington was giving a Friday evening discourse. And he was supposed to be talking about, or was talking about, the moons of Saturn, how many had been discovered. I forget, it's a tiny number compared to the, 60 odd or whatever it is we know today. So he was talking about the moons of Saturn and comets. But I love the fact that he ends his Friday evening discourse. And again, these are all here in the archive. Some of them are online as well, so you can read these. And he says, I cannot close this discourse without alluding to what is perhaps the greatest result of any that recent years have afforded to astronomy. And he talks about Hale. He has gone farther and shown, I believe, to the satisfaction of physicists, that the light passing up through these vortices bears the sure marks of having passed through a strong magnetic field. This work was so important, Eddington couldn't resist on this spot talking about it. And shortly after, George Ellery Hale was invited here to give his Friday evening discourse, and then also because of the significance of his work was invited to become a member of the RI. So his work was absolutely fundamentally important to us in solar physics, even to this day. So the sun is not only a very dynamic ball of plasma, but it's a magnetized ball of plasma. And so that's how I want to finish off in the last section of my talk, the last few slides. So my job today heavily revolves around measuring and using magnetic field data of the sun. So the kind of images that I would use are like this. So this is now a magnetic map of the surface of the sun. It shows us regions where the magnetic field points out of the visible surface, and that's shown in white. Then regions where it points in black. So that's like having a north and south pole on the surface of the sun. And there will be magnetic field going from one pole to the other. Now, of course, I can't get to the sun and sprinkle my iron filings, but what I can do is make use of this data, the strength and direction of the magnetic field, and then the physics of magnetic fields to create what we would call an extrapolation, illustrated here using the concept of magnetic field lines as introduced by Michael Faraday. So here you can see between the black and the white giant arches of magnetic field stretching out far into the atmosphere of the sun. So you cannot study the sun without thinking about or knowing and studying its magnetic fields. And as those sunspots change over time with new ones forming, old ones dying, so the magnetic field in the atmosphere of the sun and threading the surface evolves. It is a dynamic object. But once we knew about magnetic fields, we could start to understand the forms of solar activity. So the solar flares that I mentioned are interpreted as being releases of energy stored in magnetic fields in the sun's atmosphere, releases of magnetic energy, and energy that's then converted into other forms, particle acceleration and radiation. But for the form of activity that I'm most interested in, which are these coronal mass ejections, I want to show you that in a bit more detail. So this is an illustration of one quite small coronal mass ejection that happened on the sun. On the top left-hand side is an image of the sun in soft X-rays. So this is glowing hot plasma, a few million Kelvin. And then on the right-hand side in green is an ultraviolet light movie of the sunspot region that produced the coronal mass ejection. So if I run that movie, you'll see there's a little tiny flare that happens, but the magnetic field in that region reconfigures. And okay, we can't see directly the magnetic field now, but what we can see are the shapes in the plasma. And there's a really nice relationship between a magnetic field and a plasma, which is electrically charged, in that the electrically charged plasma gets trapped in the magnetic field, and it traces out its shapes in a sort of an analogous way to having iron filings. So I can look at the shapes in the magnetic field, shapes in the plasma emission, and use that to learn something about what the magnetic field is doing. So if I just run that again, you'll see that when the configuration changes, that's a change in the magnetic field. And you may also have seen a wave that comes out from that eruption as well. I'll just play it again. Does it show? Oops, is it going to play? Yeah, boom, this wave. And that's because of the expansion of this eruption. When we look at it in artificial eclipse data, so this is artificial eclipse, this is not a particularly clear movie, but you can see that material being ejected away from the sun. But we wanted to understand, or we do want to understand, and this is a worldwide effort, why does the sun suddenly erupt the mass of a mountain into the solar system at speeds of up to a few thousand kilometers a second? And in the same way that we think the energy that powers solar flares comes from the magnetic field, we also think that for these coronal mass ejections. That the sun's magnetic field is dynamic, it evolves, and it stores up free energy. But that's not enough. And a lot of the focus in recent years on understanding coronal mass ejections has been around what shapes the magnetic field takes on. So what I want to show you now is a series of images of this little region of magnetic field and plasma and how it changes over a couple of days. So here on the bottom, that's zoomed in now, and over a couple of days, so imagine you're looking down on this part of the sun. I want you to try and visualize, well, if I had an arched magnetic field with gas running along it, I would see some straight features. And that's how I interpret what we have on the left-hand side, a series of arches viewed from above. But as time goes on, over a couple of days, this whole magnetic field structure and the plasma trapped in it changes to become something that looks like an S shape. And that, I think, not all my colleagues agree, but is a signal that the magnetic field is evolving into something that we call a flux rope. So this is now, if you imagine your bundle of magnetic field lines, if I twisted them, I could make a helix or a helical shape. And a flux rope is a magnetic field configuration where the field lines are helical. And so the work that we've been doing at UCL and with collaborators is looking at the formation of helical structures in the sun's atmosphere. And we've also done modelling. This is modelling work done by Antonia Savcheva, who works in the US. And so within her computer, she again uses the physics of magnetic fields and is able to create a magnetic flux rope that we can then compare directly to the observations. So in her magnetic field line models, do we see the same shapes in the plasma emission in the sun's atmosphere? And I would argue that we do. They go from being more like a series of arches into being something that's S-shaped. So a lot of the work that we've done now around coronal mass ejections has been about the identification of flux ropes in the sun's atmosphere. And so I think this is perhaps my last slide now to illustrate why we care about flux ropes. Why should we care? Well, there's a good reason. Because if you build a flux rope in the sun's atmosphere, it has a very good chance of being able to expand upwards very quickly. And that could be the cause of the coronal mass ejection. So I've got a couple of simulations to show you to illustrate what I mean. So these are the two simulations. First of all, I'm going to play the one on the top left. And what I want you to notice, though, is that rainbow-coloured helical structure. That's the flux rope in the sun's atmosphere. Well, okay, in my colleague's computer, but anyway, simulating what's happening in the sun's atmosphere. Above it are the magnetic arches in the sun's atmosphere. But my colleague can evolve this configuration and he can make it undergo an eruption. So there you see it rising up and escaping the sun. So magnetic flux ropes are very interesting structures. And they can undergo a magnetic instability once they've formed. That means actually we can get them to erupt at very high speeds to escape the sun. Then just to show this other one, so this I really like, I find this quite compelling. So this one now, you see the twisted helical structure of the magnetic flux rope. Rising up, this time it's undergoing something that we call the helical kink instability. So as well as rising, it twists, and you see it kinking. So on the right-hand side, you've got the simulation, and on the left-hand side, you've got the solar observations of the origins of an eruption. And you can see how closely they match together. So there's a lot of work now in using magnetic field structures to explain coronal mass ejections. Okay, I think I've probably filled my time, so I just have one last slide. So I couldn't finish the talk without at least mentioning that, okay, we can look at the visible surface of the sun, we can look at the atmosphere of the sun, we can look at the atmosphere out towards the Earth and beyond, but we can also look inside the sun. So this last visualization makes use of the fact that we can probe the solar interior, where the fusion is happening to generate sunlight in the first place, and also where the magnetic field of the sun is originating. So as this movie plays, you'll see the sun spinning, and then it will open up and show us the inside of the sun. We use the technique of helioseismology to probe inside. It's a technique of using sound waves measured at the surface of the sun to look inside. The sound waves pass through the sun, pick up information about the interior layers, and then we collect it at the surface. So this is a NASA visualization that shows the outer layers of the sun. And all the lines you can see are magnetic field lines. And you'll see that they evolve over time. They become tightly packed together, and then they die away. And then they become tightly packed together, and they die away. On the right-hand side, you can also see the number of sunspots varying over time. In blue and red, you have the interior flows being indicated. And then on the left-hand side, the blue and yellow is the strength of the magnetic field inside the sun. So we see sunspots at the surface, but they begin their life as magnetic fields that get amplified inside the sun. Incredible. And actually, the origin of this work that we call the solar dynamo, the transformation of rotational energy of the sun into magnetic energy, that was carried out at Mount Wilson, which is one of the observatories that George Ellery Hale was absolutely key in. So many things track back to Hale. So I think I should probably finish on that point, but I want to say I hope that that's given you a flavour of the amount of time it's taken to come to understand something as simple as a sunspot, several hundred years, but that our modern view of the sun is that it's dynamic, it's variable, but it also has an impact on us here on the Earth. So I think I would say thank you for listening, and I can take any questions.
If you had $1 billion and you could build an instrument or a space mission to look at the sun in a new way, what would you do? What's to come next?
Yes, so I want to know more about the magnetic fields because they are so important. But perhaps there's two parts to answer that question, because in terms of what comes next that we have already got funded is a mission called Solar Orbiter, which will get very close to the sun and take images of the sun close up for the first time. So it will get into the sun about as close as Mercury is. So next Monday, when you're watching the transit of Mercury go in front of the sun, yeah, in your diaries, yeah, no?
Your man up here is nodding.
Yeah, excellent. Think about the fact that where that planet is, the closest planet to the sun, that's where we're sending our next mission. And it's a European Space Agency mission called Solar Orbiter. So my colleagues are all frantically busy building instrumentation for that at the moment. The whole spacecraft itself is being built in Stevenage. Did you know? Stevenage Centre of Spacecraft Technology, at Airbus Defence and Space. And that will launch in 2018. So the next project for us is to get up close, measure, sniff and sense that solar wind and the coronal mass ejections up close to the sun before they've evolved and before they reach us, take images close up, but also get outside of or above the plane in which the planets orbit the sun. So the spacecraft will tilt and be able to see over the poles of the sun. And that's important, actually, for these processes related to the solar dynamo, this evolution of the magnetic field, because all sorts of plasma flows are important, and we can see mostly the ones around the sun's equator, but the plasma flows up towards the poles are really important too, and we haven't been able to see that yet. In terms of what would I do, I quite fancy a mission that would just spiral into the sun until it melted or stopped working or bombarded
Like
by
the film
particles.
Sunshine, right? Get as close as you can.
Yeah, actually, yes.
On a fiery plunge of death.
Yes,
into
why
the
didn't they
sun.
take some telescopes with them?
They
Big
took Cillian
mistake.
Murphy, that was good enough for me. We will now open to the floor. If any of you have any questions at all, and in particular I'd urge, if there are any children sat in the audience, please, please, please put your hand up, because I find, I'm sure you might agree with me, Lucy, that children always have by far the best questions.
Yeah, and the hardest.
Better than any of us grown-ups and boring lumbering adults here. We have our first question up at the back, thank you.
You were talking about like solar flares and those, what are they called? Those eruption
Coronal
things.
mass ejections.
Yeah, them. Is there going to be like at some point, billions of years in the future, like a massive solar flare or ejection that like destroys the whole solar system?
So that is also a topic of research, and it's an area where people have drawn from information about other stars. So, for example, NASA's Kepler mission, which looks at visible light coming from other stars, and the main aim is to detect planets orbiting those stars. But a sort of happy consequence is that if there is a visible light flare on those stars, it will also pick them up. And indeed, it has done. So I've read a few papers now where studies have shown that sun-like stars, so perhaps ones that rotate at a similar rate to our sun with the similar characteristics, they can show flares that are thousands of times more energetic than our sun produces. And so there's one school of thought that says, okay, well, we've got a snapshot of our sun at the moment producing these fairly well-sized, nice-sized solar flares. But if we use a sample of thousands of other stars, could we then use that as a way of looking into the sun's future, capturing stars at other phases in their, or other times of their life? And so some people say yes, that if we waited long enough, we could see a supersized solar flare that might be catastrophic for us here on Earth. But my argument would be, well, we understand now that the energy to power a solar flare comes from the magnetic field. It's captured in sunspots. So in order to produce one of these really large energetic solar flares, the sun would have to produce a really large sunspot with a huge amount of stored energy in it. And I don't think at the moment, with our current understanding, that we could say that's possible. So on the short term, I don't know whether to say yes or no. Some of my colleagues would argue yes, and those who are looking at solar dynamo theory might argue no. So it's very non-committal, but I guess that's science, right? We're still asking questions, but it's a really good question. Possibly.
Do we have any more questions? What I'll do, in fact, is send 2 questions at a time so we can bounce back and forth between the microphones. Do we have any questions? In fact, Martin, we got one right at the front here, mate. Sorry, I was going to wait till you got to the top and then summon you back down, which would be a bit mean. So we'll start with you, and then we had a second question up here. Excellent.
You said at one point what you'd call the edge of the solar system. Is that just the edge of the Kuiper belt, or is it something else?
So this is another debate that I have with people, is where is the edge of the solar system? So is it where the sun's gravitational influence becomes really weak? So maybe where the Oort cloud is, 1 light year away, where the comets reside? Is it where the planets end? And that's changed because Pluto is no longer a planet. But I would say the edge of the solar system is where the sun's magnetic influence ends and plasma influence ends. So if you think back to that movie I showed with all the expanding material, we've got the sun in the center, the solar wind, its atmosphere, expands out to a distance far beyond Pluto, to around, well, in fact, we know where one bit of it ends because the Voyager 1 spacecraft passed through it in 2012, and that was around 18 billion kilometers from the sun. So for me, the solar system ends where something called the heliosphere ends. And the heliosphere is that bubble of plasma and magnetic field created by outflowing material from the sun.
Thank you.
Do you have a second question from this side of the auditorium? There's another one in the second row here, Martin, and we'll bounce up to the back.
Oh, up in the gallery too.
Have we got one up in the gallery waiting? Okay, we'll come to you second after this one up here. Thank you.
I was just interested to know if all the sun research was treating the solar system as an isolated system, and there was any thought about whether there are external influences on the sun. Obviously, physics is a contained system, or any of the quantum physics versus anything kind of more galactic was in any way an influence, or is that just too much sci-fi?
Well, it makes me think about theories of the formation of the solar system, certainly, where the idea is that there was a vast cloud of gas and dust that was incredibly thin and stretched over a very large distance, and that some external influence triggered the collapse of some part of that cloud of gas and dust. So perhaps it's the shock wave of a nearby supernova, for example. So certainly for formation of the solar system, you push on it a little bit and gradually over time, its self-gravity pulls it together to form the sun and the planets. I don't know of, I think really, well, perhaps then maybe the more modern answer would be that there's lots of research looking at particles coming from outside the solar system and the impacts they have on us. So particles called galactic cosmic rays, they get shielded to more or lesser extents by the sun's magnetic field in the heliosphere. So when the sun's at the height of its cycle with lots of sunspots, it has a strong field in the heliosphere, and that deflects the cosmic ray particles well. At times of low solar activity, the opposite is true. The field shrinks and more particles come in. So there are those kind of interactions. Then there's been studies around the motion of the solar system through the galaxy. Is there or isn't there a shock ahead of it? And then we have Voyager data now sending us direct information about what the composition of the plasma is inside the heliosphere and outside the heliosphere. So there are areas, but it's really hard to get the data, I suppose.
No, so I can't see anything up in the gallery, so this will be a voice from the heavens coming down to us.
I've heard about the flux lines. What were they called again?
Oh, the flux ropes, the twisted ones?
Yes, were they just magnetic, or do they actually have gases inside them?
Yes. So again, there's always different ways I could answer. So they are magnetic with trapped gas in them. So they are both components together. But quite often, if you speak to a solar scientist, they might be a bit more interested in the magnetic field and not talk about the gas, or they might be a bit more interested in the gas and not talk about the magnetic field. We love to simplify things. And I'm on the magnetic field side. But I do need the gas to trace out the shapes of the magnetic field. But it is important to consider both, because I talked about basically forces on the magnetic flux rope that point upwards and allow it to erupt up away from the sun. Because they actually also contain gas, they have a mass, which means they have a gravitational pull downwards. So you have a bit of a competition between forces that shouldn't be forgotten when you're really thinking in detail about it. Yeah, good question.
Excellent. We have a question down here. Do you have another question from this side? Yeah, you might as well just give it to the gentleman next to you. We'll come to you second.
Is it ever possible that the sun's magnetic field will become strong enough to rip the Earth's magnetosphere apart?
It's all doomsaying from the audience
yeah,
tonight, isn't it?
I love it.
How will the sun kill us, Lucie?
Yeah, I can. So there's a really nice piece of science that you're raising, which is how the sun is interacting with the Earth's magnetic field that we call the magnetosphere. And I sort of alluded to it, but I didn't talk about it in detail. So when you have a coronal mass ejection come towards the Earth, it can interact with the Earth's magnetic field. So the Earth's magnetic field is like a bubble around the Earth, and we're sitting then inside the bubble of the sun's magnetic field. So when we have something coming from the sun that reaches us, it can push on the Earth's magnetic field and compress it, set up electric fields, electric currents, with knock-on effects, or it can undergo something we call magnetic reconnection, which means that you get a direct connection between the magnetic field coming from the sun with the Earth. And it's easier to draw. I need to draw my field
Get your
lines.
pipe tubes out,
yeah,
Lucie.
yeah. I need
Some in your
something.
back pocket.
I should have bought some. But the basics or the overview is that if you connect up the magnetic field from the sun to the Earth, so yeah, you draw your line directly from the sun to the Earth, but that material from the sun is constantly moving. So it connects up to the Earth, but at the same time flows over the Earth. And that can have the effect of eroding magnetic field on the sun side and building it up on the night side. So you're right, you can open it up. In fact, what happens is a cycle sets up where then the magnetic field moves from the night side back to the day side, something called the Dungy cycle, understood by Jim Dungy, who worked at Imperial College. But you can compress and erode the magnetic field. Now, in terms of what we've had in the past, we have had sufficient compression and I think perhaps erosion as well, where some of our satellites that were previously inside the magnetosphere have found themselves outside and in the solar wind. But again, it's probably similar to the question about the solar flare, because it all comes down to the amount of magnetic flux and energy. So perhaps the more likely scenario over the long time scale might be also to consider changes in the Earth's magnetic field, where the Earth's magnetic field might reduce in strength when it undergoes a flip, and that maybe what you're saying would become more likely when the Earth's field reduces rather than something intensifying in the magnetic field of a coronal mass ejection.
Excellent. Am I neglecting anyone on this side that I can't see? Martin, get the microphone over here, please. We've got a question lined up, and have we got anyone up in the heavens again? Not yet. Okay.
I might have got this wrong, or you might have alluded to it already. My understanding was, from hearing somewhere, that the cycle of solar activity was related to the polarity or the sun's poles flipping over from time to time. Is that true? And does that happen on is that the regular basis for the peaks and troughs of sunspot activity? And do we understand why it's happening? And will it always carry on at the same cycle?
So you're right. The overall bipole of the sun, so you imagine it's got a big bar magnet inside, as well as the little ones on the surface of the sunspots, that flips every maximum in the solar cycle. So around the peak of the cycle, the polarities are reversed. I mean, it's not probably fair for me to say it flips like this. What happens is a reversal at the poles. And the way that we are thinking that might happen is that magnetic field that reaches the surface of the sun and forms sunspots breaks up and then starts to get redistributed over the surface of the sun. And in fact, I could probably... So even in this kind of image, you can see the strong patches where the sunspots are, but up towards the pole, especially in the northern hemisphere, you can see that there's sort of a band of black. And that's old sunspot magnetic field, which has disintegrated and been moved by plasma flows towards the pole. And the same has happened in the southern hemisphere. So what we think happens is that at the start of the solar cycle, you've got, I don't know, let's say a north magnetic pole in the northern hemisphere. But the sunspots bring up field that eventually it's so I said north. So the south magnetic pole of the emerging sunspots is what works its way up to the top of the sun. And it overwhelms the magnetic field that's there, and it has the opposite sign, and it reverses it. And the same happens in the southern hemisphere. So the reversal of the polar magnetic field is thought to be a consequence of the formation and evolution of sunspots, but at the same time allows the next cycle to play out with the opposite orientation. But to see that, we need to see the poles of the sun, really, and that's what Solar Orbiter will help us to do.
you have any questions on this side again? Yeah, go on then. And Martin, we've got one up here, haven't we? Here. Sorry, Mr. Gentleman here.
Thank you for thank you for a most excellent lecture, Professor Green. My question is in two parts, both of which I think are relatively straightforward, at least I hope they are. Could you tell me what the power of the sun is? I've always thought it to be about 10 to the 26 watts. Is there a new revised figure? And also, is it 100% efficient as regards the formula E equals mc squared?
Ooh, gosh. So for the last point, the energy generated by fusion in the core of the sun is, in each reaction, is quite small. And I forget the number, but it's the number of reactions inside the sun that adds up. Because you've got this vast interior sphere where the fusion is happening. And so, yes, I think the answer to your first question is yes. We had some new results that came out of, I think it was work by Joanna Haig at Imperial College about how much energy, or what the power is that we're receiving at the Earth, or say at the top of the Earth's atmosphere per metre squared. And I actually can't remember the number. But if you look up Joanna Haig's work, she has a publication where she talks about that. I hope that's okay.
So my favourite fact about the sun, and you might be about to tell me that this is completely rubbish, I've misremembered it, but the energy density at the core of the sun where all the fusion happening is basically the same as a compost heap, and it's just you've got the sheer volume that adds up all that energy.
Yeah, that's...
You're nodding, maybe I haven't just told
completely
right.
No, that is right, because there's a bit, I'm trying to remember what I wrote in the book as well, because so there's a lot in there. Because there's a bit where it's relevant to talk about the history of our understanding of energy and the conservation of energy. And there's a ship's doctor, Mayer, who's important in this story. So he came to the conclusion about conservation of energy from a completely different angle to, say, someone like Joule, because he was looking at the colour of blood in sailors that he was operating on. And they had different coloured blood, whether they were in warmer or cooler climates. And he had this reasoning that it was about the burning of food and literally producing ash in the blood. But I think it's the case that the energy that is generated within the sailors is because of eating food, is higher than the energy per mass than inside the sun. It's a very low it's a very low amount, but it adds up.
Sun's quite big, isn't it?
Yeah.
Will you shout at me if you have any questions from above? Because I can't see hands going up. But we have our next one from over here.
Well, it's just a very, very simple question. First of all, what type of particles, if any, could you actually measure inside this lecture theatre, when the sun was shining? So what sort of particles get right through the atmosphere, right down to the surface of the Earth? And secondly, how do these cycles that you've described today affect our ability to use the sun's energy for solar power?
Yeah. So when you say particles, you mean particles coming from the sun? Yeah. So I guess in a very large event, you might pick up some protons coming from the sun, perhaps. But what's much more likely is that the particles interact with the atmosphere, and then you get showers of protons, showers of particles. For example, neutrons is one of the particles that gets monitored and linked back to solar activity. And then I've forgotten the second question already. It was solar energy and... Yeah, tell me again.
The second question was, do these cycles you've described have any impact or effect on our ability to harness the sun's energy to generate, solar power?
Yeah, not that I know of. I think variations in the overall light output of the sun, especially in the visible part of the spectrum, is a fraction of a % over the solar cycle. So minuscule as compared to weather here. Yeah.
We are starting to run out of time, so we'll take one more question from each of the microphones. I'm trying to see who's had the hand up the whole time, and I've just been really badly ignoring. Yeah, thank you, Martin. And a question for the second microphone. Should we come down here? Thank you.
Thank you very much. Is there anything that theoretical, I'm not a physicist, but is there anything that theoretical physics can learn from this kind of observational work that might help us with, for example, controlling fusion reactions on Earth?
Yeah, that's a good question, because I think perhaps I always view things the other way around. I'm always thinking, what can I learn from fusion reactions to learn more about the sun? Yeah, so because I'm thinking about work where you would build a flux rope in your fusion facility and you would study the instabilities that it undergoes. Yeah, I don't know how to answer that question, to go the other way around. I think it's probably a reflection on being quite blinkered. Yeah. Dazzled by the sun.
And our very last question from the front here. Thank you.
Hello. I know that once a photon's created in the centre of the sun, it takes pretty much forever to get it out from the centre to the outside. Is there any borderline where it's bouncing and then suddenly it gets free and then it gets out? And can you tell where that borderline is using your electromagnetic wizardry?
Yes. Yeah. Yes. Well, I can show you a picture. And in fact,
I'm almost suspicious that's such a great question. It's almost like you planted it.
I know.
For the end of your talk.
Well, it is a really nice question. So you're right. When the photons are generated, they interact with the electrically charged particles inside the sun, and they get scattered. So, and I talked about that when I showed the artificial eclipse images. Photons from the surface of the sun, visible surface, being scattered by electrons in the plasma leaving the sun. And it's the same on the inside. So they get a sort of random walk, like a pinball effect inside the sun. But that's true when you've got a very high degree of what we would call ionization. So you've got lots of electrons that have been stripped off of the atoms. So you've got lots of electrically charged particles. As you move out through the sun, from the center outwards, the conditions change and the level of ionization changes. So once the photons have gone about 2/3 of the way through the sun, they actually start to be absorbed by ions and captured. And then those ions can take that energy with them as they move around the sun, and then they can be re-emitted and absorbed and re-emitted and absorbed. So it's really a question of something we call opacity. How easily can the light move through the plasma? And the point at which it suddenly can move freely is this point, the photosphere. So at that point, the density has dropped and the ionization level has got to the point where the photons can easily move through the gas. And the photosphere is around 500 kilometers thick. So over, it's a tiny fraction of the size of the sun. And that's why the sun looks like it's got this solid surface, because the layer in which the photons suddenly can escape is really narrow. So it sort of misleads us, because you look at this and you think, oh, that looks like a solid surface, whereas actually it's a really low density gas. But it's just that the photons can escape. Yeah, so it's happening in the photosphere. Yeah.
All right, sky for the month for May 21. Moving straight along there. First quarter moon on the 20th of the 5th, which is tomorrow. The moon is at perigee on the 26th. It's also a full moon on the 26th, and it also has a total eclipse on the 26th. So, perfect storm for us. Venus, on the 29th of the 5th, Venus will be about half a degree north of Mercury at 6 p.m. So if you hold your arm out at full length, the width of your thumb is about half a degree. So Venus will be fairly easy to spot. Mercury not so easy, but it should be just below it. And I put there Mercury in descending node. We were talking last month about the various nodes as it passed above and below the ecliptic plane. So in descending node, it means it's actually moving through the ecliptic plane to below it. Moving on into June, last quarter moon on the 2nd of the 6th, and on the 2nd of the 6th, 3rd of the 6th, and the 7th of the 6th, you've got Jupiter, Neptune and Uranus all fairly close to the moon. New moon on the 10th, so for those wanting to look at galaxies, dark sky objects, deep sky objects, that's the time to start doing it. And we have a couple of comets. A new one coming in at this stage is Comet Finley. It'll be half a degree south of NGC 474, which is a galaxy in Pisces. Okay, so for those with go-to scopes, if you type in NGC 474, you hopefully be able to see the comet. It is 10th magnitude, so it's not all that bright. And one night later, we're still in Pisces there, just below another galaxy, NGC 520. And Pons Winkie is 0.8 degrees south of the Helix Nebula, and it's about to reach perihelion, which means its closest approach, and it's down to about 8th magnitude. So probably a reasonable chance to actually see that one. The night sky, for those of you last month, you saw this slide. The beauty is I didn't have to replace it for this month. So this is the May, mostly for around about 10, 11 p.m. A couple of things of note there is, looking for, okay, you've got your Lagoon Nebula there, M8, you've got a couple of open clusters around, well, there's quite a few open clusters around the tail of Scorpio. And just a note on it, over winter, to try and star-crawl your way around the sky, it's handy if you can find an obvious constellation to base it on. And personally, I find during summer, Orion is the easiest one to find and to work your way from. And during winter, the easiest one is Scorpio. And the main reason for that is it's got a big swooping tail, which is very, very obvious, a lot of very visible stars. And then from there you can move your way around. The Southern Cross obviously is always visible, up here with the pointers. At the moment they're relatively high in the sky because they're up above the celestial pole. Now as we go around over the course of the year, what you'll find is that will turn around, and at the same time in each night is you'll see the Southern Cross and the pointers go around like this. So they're always visible in our sky, but they're at the moment particularly visible with a few things to look at around there as well. Looking to the north, the thing worth noting there is the Virgo supercluster of galaxies. These are fairly easy to find because you've got Spica and Regulus, which are two fairly bright stars. One's Alpha Leo, the other one is Alpha Virgo. And if you look at those two bright stars, the supercluster area forms a nice neat little scalar isosceles triangle with them. So if you're ever having a play with the sky watcher there, or the bead down in the observatory, maybe just have a little bit of a look at that Virgo supercluster, which looks something like that. Okay, it might not be quite that bright. Galaxies tend not to be that bright. You look through your telescope and think, I'm going to see something great, and it's a fuzzy little faint patch. This one's obviously the result of astroastronomy, but as you can see, it's a significant number of galaxies in fairly close proximity to each other. And as the supercluster, 1,300 member galaxies, 65 billion light years from Earth, 7.5 billion light years across. So you can imagine that. How big's that? It's a little bit beyond the average human to conceive. It is part of our address in the universe. Earth's in the solar system, in the Milky Way galaxy, which is part of a local group. That local group is part of the Virgo supercluster. So if you look at one of those little maps of the universe, where you've got all those strings of galaxy, of material and that sort of stuff, they're all various superclusters. We're in the Virgo one. The planets, Mercury's returned to the western evening sky. It's gone through its conjunction, superior conjunction with the Sun. It'll reach maximum elongation on the 17th. So for the newer members, that means it will be as far away from the Sun as it gets, which is not very far from Mercury, not quite like Venus. And on the 29th is when it has that close conjunction with Mercury. So remember, half a degree. It's only a thumb's width at arm's length between Venus and Mercury below it. So those wanting to see Mercury and Venus, that's a good way to find it for you. Venus, like Mercury, started to return to the western evening sky. Will start to get higher as the month goes on. It's also gone through superior conjunction, so that's why it's in the evening sky. Not much happening on Earth this month, except we do have the total lunar eclipse on the 26th of the 5th. We are having a members gathering here. As Peter said earlier, it won't be in here, it'll be out looking through the telescopes watching the eclipse. And for those who want to have a crack at photography, a lunar eclipse is not a bad one to have a go at. And as I said earlier, it'll be a full and supermoon as well. The reason it's a supermoon is it's at perihelion, which means it's closest approach to Earth. Mars is now in Gemini, which puts it fairly low on the western horizon. It's starting to get a little bit too far away to really see much detail, except unless you can book a bit of time with the Hubble. Good luck with that. Jupiter in Aquarius, rising around midnight this month. Now, when we say rising, that means it's just breaking the horizon, so it's not really going to be in a good spot to see and probably until around about 2 AM. Saturn is just a little ahead of Jupiter at the moment. The reason for that, Jupiter has gone past Saturn. Those who remember looking at them towards the end of last year will remember they were fairly close together in a conjunction. And they're moving apart now. The reason for that is Jupiter moves a lot faster than Saturn. Saturn takes 30 years to go around the Sun, Jupiter only takes 12. So technically, Jupiter's running away from Saturn. And Saturn is currently in Capricorn, will be there until 2023. Uranus went through its conjunction on the 1st of the month and will reappear as a morning object towards the end of this month. So if you really want to see a bluey-green dot, you'll have to get up in the morning to do it. Neptune has returned to the early morning sky in Aquarius after its conjunction last month, and it's rising about 2 AM, so you're probably looking at around about 4 AM before it's before we'll be able to see that little blue dot. And the appearance of the planets. Mercury moves fairly fast, so as you can see up there, by the 25th of this month, it's starting to have its back to us. The reason for that is it scoots around. It only takes 22 days to travel from pretty well maximum elongation to inferior conjunction. So it'll appear and disappear very quickly. Venus, on the other hand, it's just popped out from superior conjunction, so it's sort of on the other side of it. The Sun's here, it's out here, so we're getting a full face of Venus. But it's relative close proximity to Earth, and it's very shiny, cloudy atmosphere, tends to make it quite visible. Not that there's a lot of stuff to see with it, because of the cloud. Mars, as I said, it's disappearing into the distance. You have to wait another 2 years before it'll come back to opposition. Saturn and Jupiter are both morning objects at the moment. They're still in relative close proximity as they are with Uranus and Neptune, although Uranus, as I said, is just coming through its conjunction with the Sun. So generally, if you want to see the 4 big planets, you're going to need to get up early in the morning. No, Fred? No? Too cold? I agree.
Well, when you bring Neptune round about 8 o'clock on the night, because I know where I am. 2 o'clock in the morning, isn't it?
No worries. The other stuff this month, comet Pons-Winnicky. As I said, it's transiting the Aquila, which is sort of on the horizon. It's around about 9th, brightening to 8th magnitude as it approaches its perihelion, which is its closest approach to the Sun before it whizzes back out into the outer reaches of the solar system. Comet DLS will be visible for most of the night in Hercules, and at the moment is around about 11th magnitude. So probably something to maybe have a crack at photographing. Hercules is fairly high up, so it's not quite as horizon-y as Pons-Winnicky. The real issue is the magnitude. And Comet Finley, appearing early morning in mid-June, around about 11th magnitude, and it moves from Cetus to Pisces to Cetus. Okay, so it's sort of hanging around the two fishes. Meteor showers, the Aquarians, which are linked to Halley's Comet. In other words, we're travelling through the tail of Halley's Comet. They are visible from the 19th, the 4th to the 28th to the 5th, reaching their peak in the morning of around about 60 meteors per hour. So it's a fairly productive meteor shower. Once again, early morning effort. So maybe one morning a month, get up and have a good look. And finishing up tonight, practical astronomy. We're going to talk about finding south. How many people have a scope mounted on a mount that looks like that? None? You all bought oh, okay, there's a couple. What you're looking at is an axial mount, what's known as an axial mount. And the whole idea of the axial mount, once you mount your telescope on it, is that it's parallel to the Earth's rotational axis. And when we're talking about that, we're talking about this bit here. And the idea is, as the Earth rotates, it holds its angle, so any declination you have set will stay constant. And all you need to adjust is your right ascension. Your arc through the sky is your right ascension. But to work them properly, you need to be able to find south. And so tonight, we're going to have a little look at how to find them south, because we want this bit here pointing at the south celestial pole. Okay, so a little bit different, a few things here at the moment. So this is your actual piece here. Now that is set two ways. One, it needs to face south. Secondly, it needs to be angled to your latitude. Not everyone has a polemark in there. Okay, so once you've got that set there, that will be parallel to the Earth's axis. And rotation around that way is your right ascension, i.e. across the sky. And the other adjustment, which is this one here, will give you a motion in what's known as declination. And declination is your angle above the horizon or below the horizon. Those of you with Alhazen mounts, you can go to sleep during this, you don't have to worry about it. Okay, so one way of finding the south celestial pole is to use a couple of asterisms, a couple that are very, very easy to find. First one is the Southern Cross. Imagine it's a kite, and it's got a tail through the long axis, about 4.5 times the length of the actual cross itself. And to help you find this little point here, the pointers, if you draw a line between them, perpendicular to a line that joins them, so 90 degrees there, about where those lines meet is your south celestial pole, roughly, okay? It's not perfect, but it'll be close enough for most axial scopes and visual astronomy. The other way is to use your compass. Everyone's mobile phone has a compass on it. You hold it down and you point it south. The problem is your compass will point magnetic south. So it's not, well, if your variation was nothing, you wouldn't have a problem. But the real issue is the Earth's magnetic axis is different to its rotational axis. And depending on where you are on the Earth's surface, it will depend by how much it varies. And in Australia, this is the variation. Here we've got zero variation, and even though it's not marked on this chart, I can tell you that these variations here are variations east. And the ones over here are variations west. Now, the reason we need to know that, if you look at Melbourne, the variation is around about 11.5 degrees. So you can use 11 or you can use 12. But what you need to do is that the variation is east, magnetic is least, or variation is west, magnetic best. Essentially means if the variation is east, you need to subtract it from your true bearing. So your true bearing you want is 180 degrees. Okay? So in Melbourne, if you subtract 12 degrees, you'll finish up with a value of 168 degrees magnetic. So you need to point your telescope 168 degrees, not south on your compass.
Mark, Greg told me that most of these telescopes that we've got here were all designed for the northern hemisphere over the south. How would you sort of adjust? Would it make much difference? Because
well, if you're using an axial telescope in the northern hemisphere, you just point it at Polaris. Right. The northern hemisphere has this beautiful star stuck right in the middle of, fairly close to the North Pole, North Celestial Pole.
How much adjustment
we don't have it in the southern hemisphere because the only asterism there is octans, and most of the stars in octans are about 5th magnitude. So they're getting to the limit of naked eye viewing.
So what you're saying then, that your minus 12 from your 180, is it still be all right for that telescope?
Yeah, okay, well this is an axial telescope. This little one here. So if we're going to use it in the south, we need to point this axis at the South Pole. Alright, so it's a little bit higher, it needs to be adjusted to about 38 degrees.
38.
Okay, so now that telescope's usable in the southern hemisphere. Now we can use it in the northern hemisphere if we were in the northern hemisphere.
Same degrees.
Yeah, well, depending on what your latitude is. You adjust it to your latitude, and ideally that there will be pointing at Polaris. But that's the only real difference. So I think someone's having a bit of a Lendian, Fred. Telescopes can be used in any hemisphere. You just need to know where you're looking and where you're setting them. Alrighty? So, for those who do have actual telescopes, you need to point them 168 degrees if you're viewing around the Melbourne area. Alright? Otherwise you'll be 12 degrees away from true south. Alright, so as I said, aligning your axial mount this way is okay for visual photography, for visual viewing. Not so good for astrophotography. The reason for that being is if you haven't got it exactly spot on, you will need to also adjust your declination. The more accurate you have it, the less you'll need to adjust that declination setting as well. It doesn't really suit astrophotography. So if you want to do astrophotography, you'll need greater accuracy. You generally need an axial mount that's got a polar scope, or a Nerina-Langkate Polemaster, to actually point it exactly south, all right, at the South Celestial Pole. Greg Walton was here earlier. Greg actually wrote an article in Scorpius, and I was hoping he was going to be here so he could tell us which one it was in, but he sent it to me the other day. And it is how to find octans to enable you to actually set your polar scope fairly accurately to use it for astrophotography. The reason is that once it's set very accurately, it is aligned with the axis, and your telescope only has to track or to counter the Earth's rotation. Any questions?
Yeah, just one, Mark. When you said some of the planets should come out early in the morning. I generally get up about 6. If I got up and went outside, could I still see some of them planets at that time? You could.
Yeah, if you got up at 6 o'clock and you still had a dark sky, Jupiter is going to be fairly high. So is Saturn.
I want to have a look at Neptune. Yeah.
Well, Neptune should also be well up. Yeah. They're rising. Jupiter or Saturn's rising about midnight. So you're looking at 2 a.m. before it's a good spot. So by 6 a.m. it's going to be 4 hours even higher. So yeah, if you take the telescope out at 6 a.m. you should be able to see them really easy. Okay. As ever, tonight's information was provided from Astronomy 2021 by Wallace Dawes and Northfield. And I'm not sure whether Simon still has a couple of copies left. So, thank you.
Thanks, mate.
Thanks, Manfred.
"50 years ago this week, the world watched as the Apollo 11 crew lifted off and then landed on the moon a few days later. Much of the attention, and especially during milestone anniversaries, has focused on Neil Armstrong and Buzz Aldrin, the astronauts who first set foot on the moon. But the work and efforts of their command module pilot and crew member, Michael Collins, was crucial too. As Miles O'Brien tells us, Collins had a perspective and concerns of his own that were distinct to the mission. His profile is the focus of tonight's Leading Edge segment.
For a man spun from the rarest of right stuff cloth, Mike Collins is surprisingly humble and self-deprecating. How much of what happened to you was luck, do you think?
Luck.
Or do you believe in luck? That's another question.
Ardently, I believe in luck. Luck should be put on my gravestone.
Sure, he and his Apollo 11 compadres, Neil Armstrong and Buzz Aldrin, were all born in the same year, 1930.
We just wandered by at exactly the right moment, and that is a consummate example of luck, and more luck. I'm a big believer in luck.
But of course, they really weren't wandering. No, they were marching with a warrior's purpose. After all, luck favors the well-prepared. In 1963, he was a test pilot driven to go faster and higher when NASA selected him in its third class of astronauts. His first mission, Gemini 10, in 1966. The Gemini missions were primarily focused on perfecting orbital rendezvous and docking, the devilishly complex process of bringing two ships together in space. It consumed the time and talent of NASA's engineering brain trust. But what about spacewalking?
Well, you just kind of go out there. And we really had not thought through what just going out there meant.
And he had 2 spacewalks on his to-do list for Gemini 10.
One of the consequences of our being ignorant, I have to say, about spacewalking was I found myself outside, no handholds where I was, slippery surfaces, slipped off, went ass over tea kettle out into the unknown beyond the Gemini.
It wasn't pretty, but he pulled it off. The worst part for us, during the gyrations, his camera unmoored from its tether, sending his priceless selfies into the void. Collins became the astronaut specialist on spacesuit development. Ironically, there were a few occasions where wearing the suit during a long session in the Apollo Command Module simulator gave him claustrophobia.
I was wedged in below one of the couches and very limited space. I couldn't really move. I was almost trapped.
Something like that you probably could never confess to anybody at that time, right?
That is correct. I never confessed that to anybody at that time. I was afraid I'd be grounded.
It's the worst word a pilot can ever hear. Fortunately, he never felt the panic in space. He says he never really felt scared, but he was worried pretty much the whole time.
I think of a flight to the moon as being a long and fragile daisy chain of events. Any one of those links breaks, everything downstream from that is useless. There's so many things that can go wrong. The machinery is compact but complex, extremely complex. You can never relax, or at least I could never relax. I could never say things are going well. That was almost a jinx to say that things were going well. I might think that in the back of my mind, but really I'd be a little on edge and a little bit worried about the next little link in that chain.
When Neil Armstrong and Buzz Aldrin climbed into the lunar module and made their way toward their historic landing on the lunar surface,
Roger, Eagle, I'm done. Roger, how does it look? The Eagle has wings.
Collins remained in the Apollo command module orbiting the moon. Not the best seat on this mission, but not something he regretted.
I think you got a fine-looking flying machine there, Eagle, despite the fact you're upside down.
Surprisingly, he did not worry about whether his crewmates would land successfully.
The Eagle has landed.
But rather whether they could depart. The engine to propel them off the lunar surface was a huge exception to NASA's design philosophy of redundant systems.
It was a solitary single, one chamber. That chamber either ignited properly and got you the thrust, or it did not. If it did not, Neil and Buzz were dead on the surface. So that was a very critical worry point for me.
Did you guys talk about the possibility that you might be the guy coming home alone? Did that ever come up?
It was not something I wanted to discuss with them. Hey, Neil, suppose you're stranded forever on the surface of the moon. Would you mind terribly if I just sort of headed home? I mean, it was not the kind of thing one talked about, but it was a presence. It was there.
There was no need to have that conversation, was there?
Exactly.
Coming home alone, what would that have been like?
Well, it would have been terrible. I hate to think about it.
Tranquility Base, Houston, you're cleared for takeoff. Roger, understand. We're number 1 on the runway. Beautiful. Very smooth. Very quiet ride.
On their ride back home, they marveled at our perch in the universe. The moon was their destination, but for Collins, the real discovery was Earth itself.
Right, I've got the world in my window for change.
The moon was nothing compared to my view of home planet. It was it. It was the main chance. I'd look out the window, and there it would be, a tiny little thing. You know, you could obscure it with your thumb, but every time you put it away somewhere, it'd pop out. It wanted you to look at it. It wanted to be seen. It was gorgeous. It was tiny, shiny, the blue of the oceans, the white of the clouds, little streak of rust color that we call continents. It just glowed. Having gone out 240,000 miles and seeing it gives me a much greater sense of fragility, a much greater urge to do something to protect that fragility as we go along.
His memoir, Carrying the Fire, remains the standard by which all books authored by astronauts are judged. Right stuff meets right brain. He is the poet laureate of the Apollo astronauts, and yet one of his regrets from that era involves a lack of poetry at a historic moment. In December 1968, he was the astronaut in charge of radio communication with the crew of Apollo 8, the first voyage to orbit the moon. It was his job to give Mission Commander Frank Borman permission to fire the rocket that would give them enough velocity to escape the gravitational pull of Earth. In NASA parlance, it was called translunar injection, or TLI. It was a historic first.
So I thought, when this moment comes in history, this is it. The Pope will certainly send a message. The President will come. Sinatra will sing. There'll be some acknowledgement of it. Now, in the meantime, of course, it's up to Frank and me, and we're both right up there. We're going to handle this thing properly. So I went first. I said,
Apollo 8, you are go for TLI. Over.
And Frank rose to the occasion. He said,
Roger, understand. We're go for TLI.
That was it. That was it. That was the whole thing. That was ridiculous. I mean, what do we have all this for?
If you had to do that one over, what would you say?
I don't know. I don't know. I have to think that one over.
A few weeks later, I interviewed him again at the World Science Festival in New York City. He was ready. Here's your moment for a do-over. What would you say if you could do it again?
Uh-oh. Well, I would abide by the NASA rules, which you can't say more than, I think, 8 words in a row, and preferably they'll all be monosyllabic. But under those conditions, I would say, Apollo 8, the moon is yours. Go!
50 years ago, the moon became ours, thanks to Apollo 11. Armstrong, Aldrin, and Collins were the trio at the tip of a rocket that flew into history thanks to the concerted effort of more than 300,000 people and the consistent support of American taxpayers. When it was done, inhabitants in all corners of our fragile planet saw it as a triumph for not just one country, but for humanity as a whole.
It's one small step for man, one giant leap for mankind.
For the PBS NewsHour, I'm Miles O'Brien.
I'm Miguel Perez Ayucar, and I'm an engineer working for the European Space Agency. Lunar eclipses are quite a common event, so they happen more or less twice per year. It happens when the moon is shadowed by the shadow cone of the Earth, and the sun, the Earth, and the moon are kind of perfectly aligned in space. So today I'm going to show you a bit how we image such eclipses. The best moment, the moment where the total eclipse occurs, is a bit longer than an hour. In that moment, it's not completely dark, the surface of the moon. What we see from Earth is a glow in pinks, pink color, red colors, orange color, very beautiful. It's really the view of all the sunsets and sunrises that are happening in the Earth at the same time, projected into the surface of the moon. So it's a very unique event and very beautiful. So we have 3 setups. We have a very basic setup that is basically a tripod and a camera with low magnification. We have a second setup that is also camera and a tripod, but this camera has a photo lens. So we have a higher amplification of the image, or magnification of the image. So we can see the moon bigger in our CCD. And this is the, let's say, the more advanced setup, where we have a real telescope, full telescope, with a camera as well attached to it, taking the images. So for the very basic setup, we have a tripod, so that it gives stability to the image, and a camera on top. Probably a 35mm lens, so that we can see an ample area of the sky, and we will just leave the moon drift, and then we can compose a nice image with all the moons progressing and how the eclipse progresses. For the a bit more advanced setup, so with this type of telelens, that is something between a normal camera lens and a telescope, we can have magnifications of more or less, well, this one is 500mm, so we will have the moon that is probably a quarter of the image of on the CCD of the camera. Again, we need a tripod for stability of the image taking, and now we are going to use a device that will take the images for us, so that we don't need to touch the camera. These devices have a timer, and you can say every minute take an image of the moon. For this specific setup, as you see, it doesn't have any tracking device, and it has quite some magnification on the moon. So the moon will move really fast. So you will have to be adjusting the position of the camera by releasing the knobs of the tripod and tracking it. As well, the exposure times cannot be very long because you will really see a bit of the blurring as the moon moves in your CCD. So for the penumbral part of the eclipse and the early partial eclipse, you can use exposures of 1 millisecond up to maybe 10 milliseconds. That should be good enough with a fixed setup. For the full eclipse, total eclipse, you will have to expose a bit more, so probably up to 100 milliseconds. So there you might start seeing a bit of the blurring, and that's why if you want really sharp images of the moon, you need to go to a mount device like the more advanced setup that we have, in which we are really tracking the moon. So we need a telescope that has a quite large aperture, so we can have images that are very short exposure times to avoid any blurring for the atmosphere. So in this case, we have a kind of 1 meter focal length telescope with 25 centimeters aperture, and we have put again a reflex camera, and we'll start exposing at a regular interval. We use against an intervalometer, so a device that will allow us to not touch at all the device while the event happens. In this case as well, we have mounted it in a mount. So the mount will, we will set it up such that it tracks the moon as it progresses in the night sky. So we really will not have to touch even the tripod or any of the device during the observation. With this type of device, you will get the best images of the moon. The moon will change quite a lot the brightness during the eclipse. So we will start really bright as the full moon, and will slowly dim its light. So you will need probably to be changing the exposure time of the image. And remember that it's a slow event, so it takes it takes 5 hours for the full event to develop. So you will have time to do tests on your camera. So the best is that you try several settings until you reach an image that you like, and then you continue with that. The eclipse occurs in the night, that's clear. So it's important that you have warm clothes. Also, it's interesting if you can have some buffers that you can put on your lenses, because the dew and maybe ice, you can maybe have condensation on the lenses. So with that, you will avoid quite a big part of it. Remember as well to have your batteries ready before the event, so fully charged batteries, your SD card fully empty. You can also image the moon from inside your house if you feel like better to be inside of the house through a window. So the moon is very big, it's 0.5 degrees in the sky. So you will have some blurring of due to the thermal movement of the atmosphere, especially you have difference between the inside and the outside. But in general, the moon is big, so you will have pretty good images also from home. Of course, you will need to check first the weather forecast. We depend on the weather to take the nice images, or in fact to have any images maybe. So I wish you all clear skies. Yeah, have a great observation of the moon.
NASA has blasted off the Parker space probe and it's zooming on its way towards the sun. What will we learn when we get there? How is it going to survive the heat? And what does this all have to do with Aurora Borealis? I'm Claire Riley. Welcome to Watch This Space. Good evening from the CNET studios in Sydney. I'm Claire Riley and this is Watch This Space, the show that tells you everything on Earth you need to know about what's happening in space. And tonight we're getting up close and personal with Parker, the little probe that's going to touch the sun. The Parker Solar Probe is named after Eugene Parker, the astrophysicist who first developed the theory of the existence of solar wind. About the size of a small car, the probe is the first human-made object that will ever pass through the sun's atmosphere, the corona. Latin for the word crown, the corona wraps around the sun like a crown of burning hot plasma and extends millions of miles above the surface. It holds the key to some of the solar system's biggest secrets, like solar wind and aurora here on Earth. Thanks, Claire. She's right. Just like your friend at every summer barbecue you've ever been to, Parker is heading straight for the corona. The space probe blasted off from Florida in the early morning of August 12 in front of Eugene Parker himself and this lady, who was super psyched to be there. It's set to shoot past Venus, getting a gravity assist from our planetary neighbour on the way to make sure it gets nice and close to the sun. In November, Parker will have its first solar flyby, getting within 15 million miles of the star, but it won't stop there. It's going to pass by the sun 24 times during its 7-year mission, with a few more boosts from Venus, just for good measure, eventually getting within 3.8 million miles of the star. That's about 4% of the distance between the sun and Earth. When it does, it will be travelling at 430,000 miles per hour, setting the record for the fastest ever object created by humankind. Sorry, Jimmy, you just lost the track, mate. So, what are we going to learn when Parker starts fraternising with the sun? Well, it's all about solar wind, and we're not talking about the kind of wind you get here on Earth. Solar wind describes the charged particles that are emitted from the sun's corona and blasted out into the solar system. On Earth, the charged particles that make up solar wind zoom past us at 1 million miles an hour, quite literally. But we managed to dodge most of the damage thanks to the Earth's magnetic field. Without that field, the solar wind would tear through our atmosphere and strip away things like our ozone layer, which protects us from ultraviolet radiation. Unless, of course, you live in Australia, where ozone depletion means you can literally get sunburnt 365 days a year. But we don't miss all the effects of solar radiation down here on Earth. The charged particles that do make it through our atmosphere are responsible for natural phenomena like aurora borealis. So next time you're chowing down on a nice meal of steamed hams and watching the northern lights, you can thank solar wind for that. According to NASA, the primary goals of the Parker mission are to trace how energy and heat move through the solar corona and to explore what accelerates solar wind. And you can't do that from down here on Earth. It's going to get toasty in there. We're talking 2,500 degrees Fahrenheit or almost 1,400 degrees Celsius. Now, Parker is packed with 4 main instruments that will gather data in the corona, studying magnetic and electric fields, measuring particles, and imaging the solar wind itself. But these space instruments are going to need protection when they start passing through that blazing plasma crown. For that, NASA has designed a 4.5-inch thick thermal protection system made from everyone's favourite material, carbon. Well, more accurately, a, quote, carbon-carbon composite sandwiching a lightweight carbon foam core. That's a lot of carbon. It's also been sprayed with a special white coating to help reflect the sun's energy. Thanks to that design, NASA says the front of the shield will be able to withstand up to 2,500 degrees Fahrenheit, while the back of the shield will be able to handle a more temperate 650 degrees. So, while a trip to the sun is a straight-up 10 out of 10 on the galactic death scale for us humans, Parker is going to be A-OK. Which brings us to the space weather. Over to you, Claire. That's right, Claire. NASA says that this mission should help researchers better forecast space weather events, which can do everything from knocking out radio communications to harming astronauts in orbit and even affecting the power grid. Which leads us to our space weather forecast for today. Cloudy with a chance of plasma. It's going to be a long and intensely hot journey for the Parker Solar Probe, but from all of us here at CNET, we wish that little guy a sunny expedition. Safe travels, Parker, and take it easy on the coronas. That's it for this week's edition of Watch This Space. If you've enjoyed our broadcast, then please hit the like button on your remote and remember to subscribe to get further space news as it happens. I'm Claire Riley for CNET. Good night and Godspeed.
We all know the aurora borealis are a spectacular display happening above, but do you really know what causes it? What is the aurora borealis?
When we watch that dazzling display of light, it's actually telling us a story. It's a story that began on the sun, traveled all the way to Earth, had a series of interactions in the magnetic field, and led to this beautiful display overhead.
The aurora borealis are caused by particles, electrons and protons, blasted out from the sun in all directions and colliding with gases in the Earth's atmosphere. Those particles travel 150 million kilometers from the sun to reach Earth. That can take from 2 to 4 days. That flow of particles is called the solar wind.
A lot of particles, when they reach the magnetic field, are deflected away into space, but some become trapped in the magnetic field. And what's going on is that there's this little spark that occurs, this release of energy that we see in the form of light. And so now imagine that overhead there are billions of these tiny little sparks going on. And the sequence of light, these little flashes of light, are what we see and call aurora. So if you're living in northern Canada or northern Scandinavia, northern Russia, around the North Magnetic Pole, and you look up, what you're seeing is this waterfall of particles that are following a magnetic field line into Earth's upper atmosphere.
So why are they different colors? The Earth's atmosphere is made up of nitrogen, oxygen, and other gases, commonly known as air. The colors of the aurora depends on the gas molecules that the particles are mixing with. So green, the most common color of aurora, is a charged particle mixing with oxygen. Blue is when they mix with nitrogen.
Generally along the lower edge, we see a really intense, very vibrant purple color. That's an indication of particles interacting with nitrogen.
Astronomer and physicist Galileo actually coined the term aurora borealis in 1619. It was after Aurora, the Roman goddess of morning. He mistakenly thought that the auroras were due to sunlight reflecting from the atmosphere, according to NASA, though indigenous northerners have oral traditions about the lights that go back generations. How high up are the auroras? Aurora are between 100 and 500 kilometers above the surface of the Earth. How high is that? The International Space Station orbits the Earth at about 400 kilometers above the surface. Astronauts on the space station often get a side view of the aurora.
That's still cool too, because the side view of an aurora can give you an unbelievable show. It shows you how tall an aurora can be.
Saturn and Jupiter also have beautiful auroras, even more powerful than Earth. There is a lot of mystery around the aurora, though. Scientists are always looking at new missions to better understand the relationship between the sun and the Earth and forecasting auroras and space weather. Modern-day technology like cell phones also depend on that research, since satellites can be affected by the solar wind. So why are aurora more visible in the north? Well, most auroras occur in a band called the auroral oval. That's a huge ring of aurora above the Earth's north and south magnetic poles. The northern lights we see are just a small section of the auroral oval. Places like Alaska, Greenland, Scandinavia, and northern Canada are the perfect zone because they're close to the auroral oval. If you're at high latitudes anywhere on the planet, chances are every single night there is auroral activity overhead. When there is active space weather, it can push the auroral oval like an elastic band further south. That's when people right across Canada and even the United States can see the aurora. And let's not forget the southern lights. People living near the South Pole can see the aurora borealis's cousin, Aurora australis.
It's really, truly a scientific wonder. And there's a lot that we still don't know about when it comes to the aurora. Some of the most experienced scientists say that for every question that's answered, there are 10 more that need to be answered. It's a beautiful way to watch the sun and the earth and their magnetic connection. And it tells a beautiful scientific story.
People were out observing the aurora, and they started noticing something that was overhead as well when they were seeing the aurora far to the northern regions. It was unlike most aurora. Talked to the scientists, we didn't know what it was, and together they said, we'll keep taking observations and we'll call it Steve in the meantime. Steve is mostly a very narrow purple arc, and sometimes it has these little green features that go along with it as well that are kind of like waving fingers or a picket fence. That means that there's plasma physics happening up there to cause that light and to make these little discrete features that we don't understand yet. We now have some satellite observations from the ESA satellite called SWARM that show that Steve optically is associated with a very strong flow in the particles in the ionosphere, the upper level of our atmosphere. Steve is important for a number of reasons. It's really exciting that people armed with cameras all over the globe can capture something that we didn't fully understand and shed new light on that. It's also really exciting that this happens further to the south where there are more people, so it might be a kind of aurora that more people can see than the usual kind. We're now able to look up at the sky and see things about the aurora and this subauroral region that we never understood before. And then we can correlate that with our traditional observations and lead to greater understanding.
Hello Space Cats and welcome back to my channel. Last week NASA posted this amazing image of the aurora, Beauty and the Beast as part of their astronomy picture of the day. Hang on a second, that's not the right photo. Aurora, Beauty and the Beast, after the spectacular beauty of the aurora paired with the dangers of the mechanism creating it. But before we go into that, let me talk about magnetic fields. The Earth has a magnetic field which is so large it reaches outer space. It's generated deep within the core of the Earth, where the temperatures can be as hot as the surface temperature of the Sun. Here, the outer core is made of a liquid iron, which flows over the inner core, which is made of a solid iron. This flow generates electrical currents, which in turn generates a magnetic field. The magnetic field lines are concentrated at the north and south poles, so this is where the magnetic field strength is the strongest. But these magnetic poles are not the same as our geographical north and south poles. No, the magnetic poles are in fact moving. The north magnetic pole is slowly moving towards Russia. Back in 1980, this was moving at a speed of about 6 miles per year, which is equivalent to the height of Mount Everest. However, more recently, in the last 2 decades or so, we've seen it accelerate. It's been moving 5 times this speed now. The Earth's magnetic field acts like a shield. It protects us from solar wind and other radiation that would otherwise strip away our atmosphere and cause damage to life on Earth. The charged particles in the solar wind are accelerated along the magnetic field lines into the poles. In doing so, these charged particles, which are mostly electrons, smash into gas molecules in the upper atmosphere, and they give up some of their energy. When the molecules release this energy, it creates beautiful displays of light, which we call aurora. Collisions of different gas molecules create different colors of aurora. Oxygen makes it glow green, or sometimes red, and collisions with nitrogen make it glow blue, or sometimes purple. When aurora are really bright, they can saturate our eyes, and this makes them appear white. In fact, about 1/4 of people will only see white aurora. Normally, 3 things are required to generate aurora. Firstly is an atmosphere, secondly a magnetic field, and thirdly are particles moving along magnetic field lines. These particles generally come from the sun through the form of solar wind. But occasionally, when magnetic field lines on the sun cross over, get tangled up and reorganize themselves, it can release a huge amount of energy, known as a solar flare. These solar flares release huge amounts of particles and hence radiation into space. And when the sun's activity is high, you'll get a lot of these solar flares. This means that aurora here on Earth will be very bright and very beautiful. However, it can also interfere with our radio telecommunications here on Earth. And that's exactly what happened in 1859 during an event known as the Carrington event. The solar wind was so powerful it violently compressed Earth's magnetic field, and this generated huge electrical currents which travelled along telegraph wires. These telegraph wires then sparked up and gave telegraph operators electrical shocks. There is only so much that the Earth's magnetic field can protect us from. If we were to have a big solar flare today, it could wipe out technology. We would have big consequences for navigation and things like the compasses within our phones, within boats and airplanes, and even our 4G data could go down. But thankfully, there are measures in place to protect the Earth if such a huge solar flare were to occur. Space satellites such as ESA and NASA's SOHO mission are studying the Sun, and ESA's mission cluster is studying the solar wind so that we can predict when a solar flare will happen. This will give us advanced warning so that we can turn off electronic devices in space so that they aren't damaged if such a solar flare were to occur. Both Jupiter and Saturn have magnetic fields and aurora. The aurora on Saturn are very similar to that of Earth, but Jupiter's is quite different. We know this because on Earth, the aurora are related to the strength of the solar wind, but on Jupiter, it's pretty much always constant. Jupiter's moon Io has a lot of volcanic activity. It's extremely violent, spewing out oxygen and sulfur from hundreds of volcanoes across its surface. The atoms and electrons from these volcanoes are accelerated along the magnetic field lines into the poles, creating aurora that are beautiful from all kinds of wavelengths, from infrared to X-ray. Aurora have also been observed on Venus and Mars. But hang on a second, Venus and Mars don't have magnetic fields. They do, however, have atmospheres. On Venus, the atmosphere is able to capture the Sun's magnetic field, and moving particles on this captured magnetic field can crash into Venus's atmosphere, creating beautiful aurora. On Mars, the aurora are created by neutral hydrogen atoms. This neutral hydrogen is created from solar wind protons that capture electrons in a huge cloud of hydrogen surrounding the planet. This neutral hydrogen is traveling really fast through the Martian atmosphere and is unaffected by any captured magnetic fields.
There once was a star in a galaxy, it was named the Sun, and thankfully it weaves a solar tapestry, since particles high and low. Soon may the solar wind come to bring us plasma and magnetism, filled with hydrogen and helium, and the solar wind will blow.
The solar wind charts a course, pulling lines of magnetic force, flowing outwards from the source, throws particles to and fro.
Soon may the solar wind come to bring us plasma and magnetism, filled with hydrogen and helium, and the solar wind will blow. The earth spun with its iron core, and the solar wind knocks at the door. Magnetosphere screams no more until it must let go.
Once a magnetic line is freed, buckling under the wind stampede, it whips back with tremendous speed, sends particles to the poles.
Soon may the solar wind come to bring us plasma and magnetism, filled with hydrogen and helium, and the solar wind will blow.
The particles speed back here and ricochet through the atmosphere, exciting oxygen and nitrogen there, making those particles glow.
On and on the cycle spins, sun and earth are celestial kin, dancing to the solar wind, connected by its flow. Soon may the solar wind come to bring us plasma and magnetism, filled with hydrogen and helium, and the solar wind will blow. Soon may the solar wind come to bring us plasma and magnetism, filled with hydrogen and helium, and the solar wind will blow.
And with that evening on a solar and aurora theme, I'll officially close the meeting, and hopefully we'll see you all at another gathering here, whether it's the Eclipse coming up or the members' night this Saturday night. Thank you, everyone.